Geological catastrophes are an integral part of the history of our planet, representing moments of destruction and transformation that, despite their apparent suddenness, fit into the slow, majestic rhythm of geological time. Earth, with its age of over 4 billion years, has experienced numerous such catastrophes over millions of years, but they are not the final points in its development. Each of these events, whether a volcanic eruption, earthquake, or change in sea level, serves as a catalyst for new processes that ultimately shape landscapes, ecosystems, and even climate. For example, massive volcanic eruptions that eject tons of ash into the atmosphere can temporarily darken sunlight, causing short-term cooling of the climate. But in the long run, they enrich the soil with minerals, fostering the emergence of new forms of life. Thus, volcanoes that once posed a threat later become sources of fertility, creating conditions for the flourishing of flora and fauna. It is important to note that processes on Earth proceed at an incredibly slow pace. The millions of years required for mountain ranges to rise and collapse seem like mere moments in the context of geological time. For comparison, while human civilizations have existed for only a few thousand years, mountain formations can be created and destroyed over tens of millions of years. This sluggishness of geological processes allows the planet not only to survive catastrophes, but also to adapt to them, creating new ecosystems and altering biospheres. For instance, after ice ages, when vast territories were covered in ice, Earth recovered, and new ecosystems such as forests and prairies emerged, becoming homes for countless species. Geological catastrophes, such as asteroid impacts, also played a crucial role in the evolution of life on Earth. Approximately 60 million years ago, an asteroid impact caused a mass extinction, leading to the disappearance of dinosaurs and paving the way for mammals, including humans, who later became the dominant species on the planet. In this context, catastrophes become not just moments of destruction, but necessary stages for the renewal and evolution of life. Thus, despite their destructive nature, geological catastrophes play a vital role in shaping the biosphere and geosphere. Such changes can be both local and global, and their effects are felt over millions of years. For example, the formation of oceans and continents due to tectonic processes determines the climate and distribution of life on the planet. Each tectonic movement creates new mountain ranges and rifts, influencing atmospheric flows and climatic conditions that shape ecosystems. Therefore, geological catastrophes are not final, but part of an endless cycle of life and change. This underscores that even the most destructive events on the planet can become the basis for new lives and forms of existence. Ultimately, Earth, as a living system, continues to change, adapting to new conditions created by these catastrophes. Each such event is not only the end, but also the beginning of a new stage in the geological and biological history of the planet. The grandeur of our planet lies in its ability to overcome destructive events, transforming them into processes of creation that continue to shape its appearance and ecosystems over billions of years. In this context, geological catastrophes become significant milestones on the long path of Earth's evolution, contributing to the diversity and complexity of life that we observe today. Each of these events leaves its mark, which can be traced in geological layers, forming timescales and allowing scientists to understand how changes occurred in the past. From a gas dust cloud that formed around 14 billion years ago, the primary formation of Earth began. This cloud consisted of hydrogen, helium, and dust left over from explosions of ancient stars. Gradually, particles began to coalesce under the influence of gravity, forming larger bodies. Over millions of years, these small pieces of matter collided with each other, creating protoplanetary bodies that gradually increased in mass. During this time, the temperature on the surfaces of these objects rose to incredible values, exceeding 1,000 degrees Celsius. Each impact and collision generated a tremendous amount of heat, creating a molten sphere where melted minerals and metals mixed, forming the primary mantle and core. As the mass of Earth grew, its gravitational attraction became stronger, allowing it to hold more material. This process continued for about 100 million years, during which the first planetesimals, the size of small asteroids, formed and later collided with each other, forming larger bodies. These collisions created not only heat, but also a significant amount of energy, which ultimately contributed to the formation of the primary atmosphere. The sensation of incredible heat and constant collisions created an atmosphere of primordial cosmic chaos, from which order was slowly but inevitably born. At this time, Earth was surrounded by clouds of gas and dust, and its surface was constantly changing, creating conditions for further formation and evolution. Scientists diligently study minerals formed during this period to understand how this process occurred. For example, the analysis of ancient chondrites, meteorites that came from asteroid belts, allows us to reconstruct the conditions under which planets were formed. Approximately 200 million years after the beginning of the formation, Earth reached its current size, which is about 12,742 kilometers in diameter, and its core became massive enough to start the process of differentiation, during which heavier elements such as iron began to sink to the center, forming the core, while lighter elements rose to the surface, creating the mantle and crust. Ultimately, around 4 billion years ago, such processes led to the formation of the first continents on the surface of Earth, which became a significant milestone in the history of our planet. Due to the intense volcanic activity that persisted on early Earth, the heated surface gradually began to cool, forming the primary crust. This process began approximately 500 million years after the planet's formation, when the surface temperature dropped to 1,000 degrees Celsius. At this stage, the crust was thin and fragile, with a thickness ranging from several kilometers to 10. The surface conditions were extremely unstable. As a result of strong tectonic movements, the crust was constantly torn apart and reformed, as if the planet itself was trying to release its internal energy. This application of force created cracks and faults, which became the sites of magma extrusion. With each cooling, the surface formed the first solid rocks, such as granite and basalt, which began to serve as the foundation for future continents. Meanwhile, as the temperature continued to fall, the Earth's surface slowly descended into darkness, and its heated areas no longer glowed. As the crust cooled, more complex gases began to form in the atmosphere, such as water vapor and carbon dioxide, which later created conditions for the formation of oceans. Approximately 2 billion years after the crust's formation, the planet began to form the first organic compounds, marking the beginning of biological evolution. This primary crust, although fragile, became the basis for the entire subsequent geological history of Earth, including the formation of continents and topography. It is important to note that the primary crust was not static. It was constantly subjected to both internal and external forces, ultimately leading to the formation of a complex system of Earth's crust, consisting of continents and oceans. These processes resulted in the diversity of landscapes that we can observe today. Proto-Earth, which formed around 4.5 billion years ago, was a massive body composed of molten minerals and metals, orbiting the young sun. At that time, the solar system was a cosmic symphony, with planets, asteroids, and comets dancing in complex orbits. Among them, the planet Theia, named after the ancient Greek goddess considered the mother of Gaia, or Earth, stood out. Theia was roughly the size of Mars, and, according to astronomers, was one of many bodies forming from the remnants of the protoplanetary disk. Over millions of years, these bodies gradually approached each other, causing Proto-Earth and Theia to intersect in their orbits, becoming participants in a grand cosmic dance. Approximately 100 million years after Proto-Earth's formation, these two bodies collided in a catastrophic event that forever changed the appearance of our planet. This collision occurred at a colossal speed, reaching 32 kilometers per second, and resulted in an enormous ejection of material into space. The collision created a cloud of heated debris and gases, leading to the formation of an accretion disk around Earth, from which the Moon eventually formed. This was not just a destruction explosion, but a majestic process in which particles, instantly scattered in all directions, began to gather into a single whole, forming the satellite we know today. According to scientists, the mass of the ejected material was about 35% of Theia's mass and 10% of Proto-Earth's mass, totaling more than 33 trillion tons of material in space. These gravitational interactions caused the debris to gradually approach and coalesce around the newly formed Earth under the influence of gravity, forming the Moon, which was initially located about 100,000 kilometers from the planet. This process took around 100 years, but in the scale of the universe, it was but a moment. Meanwhile, the Moon, with its own gravity, began to influence Earth's rotation, slowing it down and causing tides. Thus, the collision of Proto-Earth with Theia not only led to the formation of our satellite, but also laid the foundation for the conditions necessary for the emergence of life on the planet. It is important to note that this event was one of the most significant in Earth's history, and its consequences are still felt today, affecting climate conditions and geological activity on the planet. After the collision of Proto-Earth with Theia, which occurred around 14 billion years ago, a vast number of debris formed in the Earth's vicinity. These debris, consisting of rocks, metals, and other materials, began to slowly coalesce into a single entity. The process of forming the Moon took approximately 100 million years, during which particles, orbiting around Earth, gradually united due to their gravity. Studies using computer models showed that during the initial stages of the Moon's formation, debris collided with each other, forming larger aggregates that subsequently grew in size. At this stage, gravity began to exert its influence. Larger objects attracted smaller ones, accelerating the fusion process. Around 7 billion years ago, when the Moon had reached a size comparable to its current one, its surface was dotted with craters formed by the impact of remaining debris. These craters, as living witnesses of its tumultuous youth, still adorn the lunar landscape, narrating the story of its formation. At some point, when the Moon reached its final size, it began to stabilize in its orbit around Earth. Over the course of 1 billion years, its orbital motion became more stable, and the Moon took its place as a faithful companion of our planet. It significantly influenced Earth's rotation, slowing it down and causing the day on the planet to become longer. Additionally, the Moon began to affect tides and currents, creating conditions favorable for the emergence of life in the oceans, which was a crucial step in Earth's evolutionary history. The influence of the Moon on climate conditions, as well as on the biological rhythms of living organisms, became evident. Many marine creatures depend on lunar cycles for reproduction and migration. As the Moon orbits around Earth, it not only illuminates the night sky, but also remains an essential element in the complex system that supports life on the planet. Thus, as a result of a long process that began with a catastrophic collision, a satellite was formed, becoming an integral part of our planet. The Moon's diameter is approximately 3,400 kilometers, making it the 5th largest satellite in the solar system. During the late heavy bombardment period, young Earth became the stage for continuous cosmic attacks that left a profound mark on its history. This phase, lasting millions of years, was characterized by numerous collisions with asteroids and comets, leading to significant changes on the planet's surface. Impacts from these celestial bodies created craters, sometimes reaching tens of kilometers in diameter, which in turn became sources of new landscapes. Each impact not only destroyed but also formed, causing thermal and mechanical changes in rock formations and creating new minerals. These processes were so intense that they resulted in the formation of giant craters filled with molten rock, which then cooled and turned into glass-like formations known as tectonic glasses. Complex interactions between heat, pressure, and chemical reactions created unique conditions where elements necessary for life could emerge. For instance, many scientists believe that it was in such conditions that organic molecules, precursors to life, could have formed. During this time, Earth experienced not only destructive events, but also constant transformations, as volcanic activity released vapors and gases into the atmosphere, forming primary climatic conditions. Air masses saturated with water vapor created clouds and precipitation, contributing to the formation of the first water bodies. These primary oceans became the sites of chemical reactions, leading to the formation of the first simple organisms. As the landscape continually changed, Earth became increasingly diverse, with volcanoes, mountain ranges, and plains emerging on its surface. For example, Mount Everest is a result of tectonic processes caused by the collisions of continental plates that occurred during this period. Each new collision could lead to abrupt changes in ecosystems, creating conditions for the evolution of various forms of life. This was a time when Earth was constantly tested, but it was in this chaotic environment that the foundations for future existence were laid. Gradually, over millions of years, the planet calmed down, but the traces of these cosmic attacks remained forever, imprinted in the geological layers. Moreover, the study of these layers allows scientists to reconstruct the history of Earth and its evolution, opening new horizons in understanding how life could have emerged in such harsh conditions. Each crater, each rock bears witness to those distant times when Earth was not just a planet, but a true battlefield for celestial bodies. The atmosphere of the earliest Earth was completely alien to modern humans. Around 4 billion years ago, when the planet was just beginning to form, its atmosphere was filled with heavy gases such as carbon dioxide, methane, ammonia, and water vapor. Oxygen was virtually absent at this time. These conditions were completely inhospitable to life as we know it today. Instead of a blue sky overhead, inhabitants of this world, if they existed, would have gazed upon a reddish veil pierced by electrical discharges that could result from frequent storms and tempests. Lava flows cascading onto the surface released toxic fumes capable of killing any living organism. Surface temperatures could reach over 1,000 degrees Celsius, creating a true hellish atmosphere. This world served as a stage for chemical reactions that would later form the basis for the emergence of life. For instance, the interaction of methane molecules with water vapor could lead to the formation of simple organic compounds. These compounds, in turn, would become building blocks for more complex molecules capable of self-replication. While Earth was surrounded by clouds of acidic rain, its surface was forming the first minerals, such as pyroxene and olivine, which laid the foundation for the formation of continents. Over millions of years, these minerals were subjected to weathering and interacted with atmospheric gases, creating new compounds like clays. This was a time when Earth had no living organisms, but was already gathering all the elements necessary for their appearance. Without oxygen and with an aggressive atmosphere, ancient Earth was a testing ground for chemical experiments, where each reaction could be a step towards new evolutionary changes. Scientists like John Griffin, studying the isotopic composition of ancient minerals, concluded that it was during this period that the active formation of the first oceans began, which are believed to have played a key role in the emergence of life. These oceans contained numerous dissolved minerals that could participate in chemical reactions leading to the formation of amino acids. The spectra of these chemical processes are preserved in the rocks we find today. Complex molecules formed in these primordial oceans became the precursors to the first prokaryotes, which appeared on Earth around 3.5 billion years ago. Primary oceans filled the planet's lowlands when water, brought by comets and asteroids, rapidly filled the depressions on Earth's surface. Around 4 billion years ago, during a period known as accretion, comets, primarily composed of ice and carbon compounds, collided with young Earth, leaving traces of water. These comets, such as Hale-Bopp, contained significant amounts of frozen molecules that, upon impact, released water and other chemicals into the atmosphere. As a result, vast water bodies formed, which, according to geological estimates, covered up to 90% of the planet's surface. The primary water had a greenish hue due to the presence of various dissolved minerals, including iron, magnesium, and sulfates. These minerals, reacting with sunlight, created diverse colors, making these oceans unique and unlike modern ones. The chemical composition of this water included not only H2O, but also numerous other chemicals such as ammonia, methane, and carbon dioxide, which contributed to the formation of more complex organic molecules. During the oxidative reactions occurring in the primary oceans, important biomolecules such as amino acids and nucleotides were formed. These molecules became the foundation for subsequent biochemical processes that led to the emergence of the first forms of life. Research indicates that it was in these conditions that the formation of microorganisms, such as archaea, occurred. These archaea are among the oldest known living organisms on Earth and can survive in extreme conditions, highlighting the importance of primary water as a habitat for the beginning of life. According to scientists, such oceans could have existed for up to 1 billion years, creating ideal conditions for chemical evolution. Scientific data suggests that these primary oceans played a crucial role in shaping the atmosphere, enriching it with oxygen and other gases, which ultimately led to the development of complex ecosystems. A significant amount of minerals present in the primary waters, including silica and clay, served as the basis for the formation of the first organic compounds, which then gave rise to the emergence of living organisms. The Earth's crust is divided into numerous moving sections known as tectonic plates. These plates slowly drift over the magma layer of the mantle, which lies beneath them, at a distance of approximately 2.5 to 3 kilometers. The movement of the plates occurs at a speed of 1 to 10 centimeters per year, which at first glance seems insignificant, but over millions of years. Plate tectonics explain how mountain ranges, oceanic trenches, and earthquakes are formed. During this slow movement, the plates collide, diverge, and interact with each other, causing complex geological processes. For example, when one plate subducts under another, it leads to the formation of deep oceanic trenches, such as the Mariana Trench, which reaches a depth of over 10,900 meters. At the same time, when plates collide, mountain systems like the Himalayas are formed, resulting from the collision of the Indian and Eurasian plates about 50 million years ago. This process never stops, and as a result of the constant movement, the Earth's surface changes and evolves. Scientific research shows that plate tectonics also affects the climate, as the change in the position of continents can alter ocean currents and atmospheric conditions. For example, around 100 million years ago, the supercontinent Pangaea began to break apart, leading to changes in the climate and ecosystems on Earth. Each element of this process requires millions of years, but the results are visible today. Earth's volcanoes, such as Kilimanjaro or Eyjafjallajökull, are direct consequences of tectonic activity. Volcanic activity, in turn, influences the composition of the atmosphere by releasing carbon dioxide and other gases. Studies show that such eruptions could have affected mass extinctions, such as the extinction of dinosaurs, which occurred around 60 million years ago. Plate tectonics is not just a scientific concept. It is the key to understanding the dynamics of the planet, which is constantly changing under the influence of powerful geological forces. These forces shape the landscape, create and destroy ecosystems, and influence life on the planet. It is important to remember that tectonic processes occur not only on the surface, but also in the depths of the Earth, where temperatures reach more than 1,000 degrees Celsius, creating conditions for the melting of rocks and the formation of magma. Plate tectonics was first proposed in the early 20th century by the German geophysicist Alfred Wegener, but it was only in the middle of the 20th century that it became widely accepted 20th century, with the development of technologies such as seismology and geoinformatics, that scientists were able to convincingly confirm his theory. As a result, tectonic activity continues to be an active area of research, as it affects the lives of billions of people living on the Earth's surface and the state of ecosystems with which they interact. Subduction is a process in which one tectonic plate slowly descends beneath another, returning to the Earth's mantle. For example, an oceanic plate like the Nazca Plate collides with a continental plate, such as the South American Plate, creating fault zones known as subduction zones. This process begins with the accumulation of stress between the plates as the upper plate moves over the lower one, causing extension and compression in the contact area. Over millions of years, as the plates slowly move, this stress accumulates, potentially leading to catastrophic consequences. Pressure can build up until there is a sudden release, causing earthquakes. The study of such events has become possible thanks to seismic observations and modeling. For instance, the earthquake in Tohoku in 2011 was a result of subduction, when the Philippine plate descended beneath the North American plate. This earthquake, with a magnitude of 9, also triggered a powerful tsunami that claimed more than 20,000 lives. However, earthquakes are not the only consequence of subduction. Where one plate descends beneath another, the mantle melts, leading to the formation of magma. This magma can rise to the surface, forming volcanoes. For example, the Andean volcanic arc along the western coast of South America was formed due to the subduction of the Nazca Plate beneath the continental plate. In such areas like Chile, active volcanoes such as Villarrica serve as constant reminders of the powerful geological processes occurring beneath the Earth's crust. Subduction also influences the formation of geological structures such as mountain ranges. When one plate descends beneath another, it can lead to the formation of folds and faults in the upper plate, creating majestic mountain ranges like the Alps or the Himalayas. In the Himalayas, for example, the Indian plate collides with the Eurasian plate, resulting in the formation of the highest mountain range on the planet. These processes not only shape the landscape, but also have deep implications for ecosystems and climatic conditions. For instance, volcanic activity can release large amounts of ash and gases into the atmosphere, affecting the region's climate. In 1991, the eruption of Mount Pinatubo in the Philippines caused global cooling for several years due to sulfur gas emissions. Subduction, therefore, is a key part of the geological cycle, determining not only the structure of the Earth, but also life on it. It creates unique ecosystems on continents and in oceans, and influences climatic conditions on the planet. Interestingly, according to data from the U.S. Geological Survey, about 90% of all earthquakes occur in subduction zones. This underscores the importance of studying these processes for predicting and minimizing the consequences of natural disasters. Oceanic crust spreading is a process that occurs at the boundaries of tectonic plates, where magma rises from the Earth's mantle through faults, forming new oceanic crust. This phenomenon can be observed in regions such as the Mid-Atlantic Ridge, which extends for more than 16,000 kilometers from the Arctic Ocean to the Southern Ocean. During the spreading process, magma emerges to the surface through rift zones, forming underwater volcanoes and new sections of oceanic crust. For example, around 2,000 years ago, active volcanic activity in the region led to the formation of significant volumes of basaltic crust. The process begins with the movement of tectonic plates, creating cracks in the ocean floor. In these faults, the pressure on magma becomes low enough for it to rise. The temperature of the magma typically ranges from 1,000 to 1,400 degrees Celsius. Upon reaching the surface, the magma cools rapidly, forming new rocks. These rocks usually have low density and high iron and magnesium content, making them the primary components of oceanic crust. Underwater volcanism plays a crucial role in creating new ecosystems. For instance, around black smokers, which form as a result of spreading, unique life forms develop, including giant tube worms and bacterial colonies that can live without light, using hydrogen sulfide as an energy source. These organisms form the basis for complex ecosystems that, in turn, support other forms of life. Spreading not only creates new crustal sections, but also slowly moves continents apart. For example, modern research shows that the Atlantic Ocean is expanding by 2 centimeters per year, gradually increasing the distance between America and Europe. This phenomenon can be tracked using GPS technologies, which allow scientists to accurately measure the movement of plates. Spreading of the oceanic crust is also accompanied by seismic activity. According to the U.S. Geological Survey, Approximately 30% of all earthquakes are related to plate movement and spreading processes. As a result, some underwater volcanoes can become active, leading to the formation of new islands or changes in the underwater landscape. For example, in 2011, a volcano on the underwater Cadena Ridge in the Pacific Ocean unexpectedly became active, resulting in the formation of new land that later became known as the Nicobar Islands. Therefore, oceanic crust spreading is not only a geological process, but also a significant factor influencing the biosphere and climate of Earth. The formation of new crust and the movement of continents occur over millions of years, but the effects of these processes can be observed today. Approximately 30% of Earth's surface is covered by oceanic crust, and this percentage grows annually due to spreading. This creates new opportunities for studying and understanding the processes occurring on our planet. Supercontinents are significant landmasses that form and disintegrate over millions of years due to tectonic processes. This cycle of land unification and division occurs in accordance with the movement of lithospheric plates, causing global changes in the planet's geography. For instance, over the past 200 million years, several supercontinents have existed, combining a large portion of Earth's land. The formation of supercontinents can take up to 100 million years, after which they begin to disintegrate under the influence of mantle activity and tectonic forces. Each unification of land has a significant impact on the planet's climatic conditions, as a large land area can alter the distribution of solar light and atmospheric pressure, creating new climatic zones. When supercontinents exist, they can block or alter ocean currents, which in turn affects the temperature of seas and the formation of ecosystems. For example, during the existence of supercontinents, numerous internal seas were created, contributing to the formation of unique ecosystems that isolated various groups of organisms from each other. This led to the evolution of new species that could not meet others in conditions of isolation. After the disintegration of supercontinents, when the land is once again divided into smaller continents, the opposite process occurs. Ecosystems begin to connect, creating new biological interactions. This interaction can lead to the migration of species, which often results in competition and, consequently, the survival of the most adapted. A crucial point is that the cycles of unification and disintegration of supercontinents not only shape the geological structure of the planet, but also have a profound impact on biological diversity. Periods of isolation can provoke adaptation of organisms to specific conditions, while the connection of land allows for the exchange of genetic material between different groups, increasing biological diversity. Thus, each new supercontinent contributes to the evolutionary history of Earth, creating unique conditions for life. The average lifespan of supercontinents is around 100 million years, making this process extremely important for understanding long-term changes on the planet. Supercontinent Pangaea formed around 300 million years ago and existed until approximately 250 million years ago, at the end of the Permian period. In shape, Pangaea resembled a colossal, slightly curved lotus flower stretched along the equator, surrounded by the ocean Panthalassa. This single continent occupied nearly the entire land surface of the planet, uniting present-day Africa, South America, North America, Europe, Asia, and Australia into a single landmass. The climate on its territory was extremely diverse, but a distinctive feature was the aridity of the central part of the continent, where vast deserts were located. The central zone, lacking access to oceanic air masses, experienced sharp temperature fluctuations, with hot days and cold nights, making this region virtually uninhabitable. On the coasts of Pangaea, the climate was milder due to the influence of the ocean, where monsoon winds brought seasonal rains and created conditions for dense forests and diverse flora. However, despite the presence of humid tropics on the coasts, the majority of the interior of the continent was under the influence of arid climate, which limited the development of ecosystems. Temperate climate was absent on most of the land, which contributed to the formation of unique ecosystems, but also posed difficulties for many animal and plant species that could not adapt to such harsh conditions. On Pangaea, giant reptiles, such as the ancestors of dinosaurs, evolved in conditions where the abundance of resources on the coasts could not compensate for the lack of moisture in the central regions. Inland seas and lagoons surrounded the continent, creating a complex ecosystem where aquatic and terrestrial organisms interacted, but many species remained isolated due to the vastness of the land. As a result of such climatic conditions and geographical structure, Pangaea became a stage for intense evolution. But towards the end of its existence, as the continent began to break apart, climatic changes led to mass extinctions, including the well-known Permian extinction, when around 90% of marine species and 75% of terrestrial species disappeared. The breakup of Pangaea began around 180 million years ago and continued over the course of tens of millions of years. This process was the result of tectonic activity, as the movement of lithospheric plates led to the formation of cracks in the single continent. Initially, small fractures began to deepen, and then narrow seas formed, which later expanded into wide oceans. An example of such a change is the formation of the Atlantic Ocean, which arose as a result of the separation of continents that now separate modern America from Europe and Africa. Around 130 million years ago, when Pangaea was already beginning to break up into smaller continents, a sea known as Tethys formed, which separated Laurasia in the north from Gondwana in the south. Over time, this sea became more extensive, and as a result of its expansion, vast marine spaces were created. The process of breakup was accompanied by numerous geological events. At the beginning of this period, around 160 million years ago, there was a significant uplift of the continents, which improved conditions for the formation of new ecosystems. Initially, continents moved apart slowly, and narrow strips of water formed between them, which became wider over time. Around 100 million years ago, continents began to move at an increased speed, leading to the formation of new oceanic basins. At this time, Laurasia, consisting of North America and Eurasia, continued to separate from Gondwana, which consisted of South America, Africa, Antarctica, Australia, and the Indian subcontinent. The association of continents such as South America and Africa became less pronounced, leading to the formation of the Atlantic Ocean. Around 90 million years ago, on the site where Pangaea once stood, a new oceanic tectonics formed. This change had a direct impact on the climate, which in turn facilitated further evolution of flora and fauna. During the separation of continents, significant volcanic eruptions occurred, which also altered the landscape and climate, creating new ecosystems and intensifying tectonic activity. As continents moved apart, new oceanic ridges formed on their borders, contributing to further breakup. Around 80 million years ago, the formation of the Indian Ocean began, which separated the Indian subcontinent from Africa. This grand process, spanning tens of millions of years, became the basis for the formation of the modern continents and oceans that we know today. The division of Pangaea not only changed the geographical configuration of the Earth, but also had a significant impact on climatic zones, making them more diverse. This led to the appearance of new species and the disappearance of others that could not adapt to the changed conditions. By the end of the Mesozoic period, continents had already significantly changed from their original form, and new oceans such as the Atlantic and Indian became important elements of the planet's geographical appearance. The formation of the Atlantic Ocean is a process that began more than 100 million years ago, when continents began to gradually drift away from the single supercontinent Pangaea. This process started in the Jurassic period, when a narrow strait formed between present-day Africa and America. Around 130 million years ago, at the beginning of the Neogene period, this strait began to widen, leading to the formation of the first oceanic crust. The increase in the distance between continents facilitated the formation of new ocean currents, such as the Gulf Stream, which began to form as a result of the interaction between cold and warm waters. As the Atlantic Ocean expanded, the speed of these currents increased, significantly influencing the climate of the surrounding continents. For example, the warm waters of the Gulf Stream soften the climate in Western Europe, creating milder winters compared to other regions at similar latitudes. Around 70 million years ago, as the ocean continued to grow, these climate changes led to the emergence of new ecosystems, both on land and at sea. The diversity of marine life began to change, as new marine routes facilitated the migration of various species. For instance, species such as dolphins and sharks began to actively expand their ranges, using new migration routes linked to changes in currents. Around 40 million years ago, when the Atlantic Ocean reached its modern size, new ecological interactions between species emerged, contributing to the development of more complex ecosystems. These changes also affected climatic conditions, which in turn spurred the development of new marine organisms, including numerous types of plankton that became the basis for food chains in the ocean. By the end of the Cretaceous period, the Atlantic Ocean had become not only a significant geographical object, but also a key element in the formation of the biosphere, particularly in terms of climate change and biological diversity. Each change in ocean currents created new conditions for life, promoting adaptation and evolution of the organisms inhabiting its waters. Thus, the Atlantic Ocean has become a stage for numerous ecosystems that continue to evolve and adapt to changes in the surrounding environment. Volcanism is a process by which the internal energy of the Earth finds an outlet through cracks in the crust, expelling molten rocks known as magma to the surface. This magma is formed as a result of the melting of rock formations in the mantle, where temperatures can reach thousands of degrees Celsius. When the pressure inside the Earth becomes excessive, magma rises to the surface, creating tension between the internal forces of the planet and the crust that holds them back. This process is accompanied by the formation of various geological structures, such as shields, domes, and volcanic cones. Volcanism can manifest in various forms, from quiet lava flows to powerful explosive eruptions. Remarkably, over the past millions of years, humanity has observed numerous such eruptions that have altered the landscape of the planet and significantly influenced the climate and ecosystems. For example, the eruption of the Krakatoa volcano in 1883 caused global cooling, changing temperatures on the planet by several degrees for a year. The internal forces of the Earth continue to operate, creating conditions that can lead to new eruptions, and this dynamism remains one of the most powerful and unpredictable forces on the planet. The accumulation of magma in underground reservoirs increases pressure, which often leads to earthquakes preceding eruptions. Volcanism also plays a crucial role in the cycle of the formation of new mountain systems, such as the Andes and Himalayas, which were formed as a result of tectonic processes. These processes continue to this day and create unique geological conditions that attract the attention of geologists and researchers. Approximately 70 active volcanoes on the planet are constantly in a state of readiness, poised to erupt at any moment, highlighting the level of risk associated with volcanic activity. Each of these volcanoes is not just a mountain, but a complex mechanism where internal forces collide with external ones, creating constant tension that awaits its release. Trap volcanic activity represents one of the most significant and impressive processes on Earth, manifesting as large-scale outflows of basaltic lava that form extensive and flat plateaus. These eruptions occur when magma from the Earth's mantle rises through cracks in the crust and melts, forming lava that can flow from faults over an extended period. One of the most famous examples of trap volcanic activity is the Siberian traps, which emerged around 250 million years ago at the end of the Permian period. These eruptions were so massive that they covered an area of over 1 million square kilometers, creating thick layers of basalt up to 1,000 meters thick. The lava that flows from these volcanoes has low viscosity, allowing it to flow slowly and evenly over the surface, layering one layer on top of another to form stepped plateaus that can extend for hundreds and thousands of kilometers. As a result of these processes, characteristic geomorphological features are formed, such as the Plateau of Konar in India, where basaltic layers form elevated areas resembling giant steps. These plateaus not only impress with their size, but also play a crucial role in ecosystems, creating unique habitats for various animal and plant species. Trap volcanoes, as a rule, have relatively calm eruptions, allowing lava to slowly and evenly fill the surrounding space. However, despite this, during the formation of such plateaus, powerful gas emissions with high toxicity can occur, which can significantly impact the climate. Research shows that such events can cause abrupt changes in the environment, including mass extinctions of species, as occurred during the Permian extinction, when it is estimated that over 95% of all species perished. Trap volcanic activity is an important aspect of the geological history of Earth, not only shaping landscapes, but also altering climatic conditions on the planet. As a result of such processes as the eruptions in the Siberian traps, a massive amount of carbon dioxide was released, contributing to global warming. Throughout the history of Earth, trap volcanic activity has occurred several times, leaving behind traces in the form of such plateaus as the traps in Greenland and the traps on the Arabian Peninsula. These geological formations become objects of study for geologists and paleontologists who investigate them to understand how volcanic activity influences life on Earth. Currently, trap volcanic activity continues to be studied, and new discoveries, such as the finds in the Slovak region where ancient lava flows were discovered, testify to its significance in shaping the modern landscape. Trap formations not only represent an impressive sight, but also serve as important indicators of the geological changes that have occurred on the planet over millions of years. Siberian traps are one of the largest volcanic formations on Earth, covering an area of around 1 million square kilometers, and they formed approximately 160 million years ago at the end of the Jurassic period. These formations resulted from massive volcanic eruptions when magma rose to the surface, creating layers of basaltic lava that, in turn, formed extensive plateaus. The Siberian traps are renowned for their colossal volumes of erupted materials, estimated to be in the tens of thousands of cubic kilometers, making them one of the largest volcanic events in the history of our planet. The eruptions were so powerful that their effects were felt globally, leading to catastrophic changes in climate. Volcanic ash and gases released into the atmosphere created a volcanic winter effect, where sunlight barely pierced through clouds filled with particles and gases such as sulfur dioxide and carbon dioxide. This caused a sharp drop in temperatures, leading to mass extinctions of species and significant changes in ecosystems. Studies by scientists like Dr. Andrei Kuznetsov from the Institute of Geology of the Siberian branch of the Russian Academy of Sciences show that these eruptions could have lowered the planet's temperature by several degrees, resulting in global consequences for the flora and fauna of the time. Complex processes associated with volcanic activity also contributed to the formation of mineral deposits, such as nickel and platinum, making the Siberian traps important not only from a geological, but also from an economic perspective. Moreover, these gigantic formations serve as evidence of how volcanic activity can influence climate change, creating conditions that lead to the extinction of a large number of species, such as dinosaurs, at the end of the Cretaceous period. The Siberian traps remain not only objects of scientific study, but also reminders of how powerful natural phenomena can shape our planet, leaving behind traces that we can still research and study today. The height of the basaltic layers in some places reaches several hundred meters, and their age makes them witnesses to ancient catastrophes and changes in the biosphere. Siberian traps had a significant impact on the Permian extinction, one of the most catastrophic events in Earth's history, which occurred around 2,000 years ago, 150 million years ago. The volcanic activity associated with the formation of traps led to the release of enormous volumes of carbon dioxide and sulfur gases into the atmosphere. This resulted in a sharp increase in the concentration of carbon dioxide, which in turn caused global warming. studies show that the temperature on Earth could have risen by 10 degrees Celsius or more, which was a catastrophic blow to ecosystems adapted to more stable climatic conditions. As a result of this warming, ocean acidification began, leading to the mass death of marine organisms such as corals and mollusks, which could not adapt to the changed conditions. Scientists like geologist Dr. Daniel Godfrey assert that such changes in ocean chemistry were responsible for the disappearance of up to 95% of all marine species. Additionally, the increase in carbon dioxide content in the atmosphere contributed to the development of the greenhouse effect, which further exacerbated climate changes. These changes caused sharp fluctuations in sea level, which also negatively affected terrestrial ecosystems, as many species could not migrate in search of more favorable conditions. Consequently, mass extinctions of flora and fauna occurred on land, and this was not just a local process, but a global catastrophe. Volcanic gases such as sulfur dioxide also created acid rain, which further destroyed ecosystems and worsened living conditions. Ultimately, the Permian extinction was the result of a complex chain of events caused by volcanic activity, where each detail, from changes in atmospheric composition to ocean acidification, played a role in the formation of one of the greatest catastrophes in Earth's history. According to estimates, this event led to the disappearance of more than 13,000 species, making it the largest mass extinction in the history of our planet. Mass extinctions are events where numerous species of living organisms disappear simultaneously on a planet, caused by various factors, both natural and anthropogenic. Over the past 450 million years of Earth's existence, according to paleontologists, at least 5 such events have occurred, each leaving an indelible mark on the planet's history. During these extinctions, not only individual species but entire groups of organisms perished, leading to significant changes in ecosystems. These events often occurred as a result of global catastrophes, such as climate change, meteorite impacts, or volcanic activity, which destroyed familiar habitats and sharply reduced biodiversity. For example, the impact of a meteorite, as it is believed, caused the extinction of dinosaurs around 66 million years ago, when a catastrophe altered Earth's climate. This extinction resulted in the disappearance of around 75% of all species, creating space for the emergence of mammals and, ultimately, humans. Other mass extinctions, such as the Permian or Triassic, also demonstrate how fragile life can be in the face of global changes. For instance, during the Permian period, which ended around 250 million years ago, more than 90% of marine species went extinct due to a combination of volcanic activity and changes in ocean chemistry. Such events underscore how quickly ecosystems can change and how vulnerable they are to catastrophic factors. A key aspect of mass extinctions is that they not only destroy existing species, but also create new ecological niches, allowing surviving forms of life to adapt and evolve in entirely new conditions. In this context, life on Earth is in a constant struggle for survival, where even minor changes in climate or the environment can lead to catastrophic consequences. Paleontological research shows that after each mass extinction, nature requires millions of years to restore biodiversity and fill the gaps left by the vanished species. For example, after the Permian extinction, ecosystems began to recover only during the Triassic period, which took more than 100 million years. This indicates that life on Earth, despite its remarkable diversity and adaptability, remains susceptible to random and unpredictable changes that can wipe out entire species in an instant. Mass extinctions serve not only as a lesson on the fragility of life, but also as a reminder that Earth is a dynamic system where each change can lead to unforeseeable consequences. Given the speed of changes in the modern world, from global warming to the loss of biological species, it is reasonable to expect that we are on the brink of a new mass extinction that could have as devastating an impact on our planet as the events of the past. Studies show that more than 30% of species on Earth are at risk of extinction, creating worrying parallels with historical mass extinctions. The Permian extinction, which occurred around 250 million years ago, is considered the most catastrophic of the known mass extinctions, during which up to 96% of marine and 70% of terrestrial species disappeared. This catastrophic process spanned millions of years and was the result of a combination of factors, including volcanic activity, climate change, and an oceanic anoxic event. Volcanic eruptions in the region of present-day Ural, known as the Siberian Traps, released a massive amount of carbon dioxide and sulfur, leading to global warming and changes in the chemical composition of the atmosphere. As a result, the planet's temperature increased, and oxygen levels in the oceans decreased, leading to the mass extinction of marine organisms. Groups such as trilobites and brachiopods, which were the main inhabitants of marine ecosystems, disappeared. At this time, there was also a significant reduction in the diversity of coral reefs, which had served as homes for numerous marine species for millions of years. On land, ecosystems also underwent significant changes. Hundreds of species of ancient reptiles and amphibians went extinct, leaving ecosystems desolate. Forests, once teeming with life, became rare and isolated, leading to the disappearance of entire groups of plants, such as giant ferns and horsetails. The Permian period ended with a colossal loss of biodiversity, and many ecosystems never fully recovered. Studies show that it took millions of years for ecosystems to recover from this mass extinction. Scientific data indicate that life on Earth never returned to its former diversity after the Permian extinction, and new species, such as dinosaurs, only appeared millions of years later. The Permian extinction serves as a crucial lesson about how quickly life on the planet can disappear when catastrophic ecological changes occur. Current research shows that modern humanity, despite scientific and technological advances, is at risk of repeating stories similar to the Permian extinction due to anthropogenic changes in ecosystems. After the Permian extinction event, which occurred around 250 million years ago, Earth entered a period where life remained in a state of deep depression for a long time. The elements of ecosystems, once abundant and diverse, became desolate. The food web, composed of numerous interconnected species, significantly simplified. In place of the once diverse marine ecosystems, only a few surviving groups of organisms remained. For example, trilobites, which dominated the seas, disappeared, giving way to new forms of life. During this period, known as the Triassic, ecosystems began to slowly recover. As a result of the extinction, many ecological niches were vacated, and new species began to occupy these voids. Among the first survivors were reptiles, which began to evolve, adapting to the changed conditions. An example of this is the group of archosaurs, the ancestors of dinosaurs, which appeared around 230 million years ago. Their diversity became the foundation for the future dominance of dinosaurs during the Mesozoic era. Meanwhile, in the marine waters, new organisms began to develop, such as crustaceans and mollusks, which occupied the niches left by the extinct species. According to research conducted by paleontologists such as Dr. John Hopkins from the University of Cambridge, these changes in ecosystems led to the emergence of simpler and more resilient food chains. The simplification of the ecosystem facilitated the adaptation and reproduction of newly formed species, filling the ecological niches. For example, some fish species, such as the ancestors of modern sharks, began to develop in conditions where competition was minimal. Meanwhile, mammals remained small and insignificant, while reptiles took a dominant position due to their ability to quickly adapt and their diversity of forms. Thus, over millions of years after the Permian extinction, Earth underwent a true evolutionary reboot. This process took around 100 million years before ecosystems began to regain their diversity. The appearance of the first dinosaurs, such as Archaeopteryx around 150 million years ago, became a symbol of a new era. During this time, new ecosystems began to form on Earth, combining features of both ancient and new forms of life. This was a period when life on Earth began to accumulate diversity, creating new ecological connections and food chains. An important fact is that during this transitional period, ecosystems were more vulnerable to changes, as they were only beginning to restore their biological diversity and complexity. The situation where a small number of species dominated in ecosystems led to the fact that any changes in the environment could have catastrophic consequences. For example, threats such as climate change or sudden temperature fluctuations could easily lead to a new extinction. Research shows that such changes in climate, including global warming, were the cause of the subsequent extinction of dinosaurs around 65 million years ago. Evolution, despite its complex mechanisms, always remains dependent on the conditions in which it occurs, and each new stage in the history of life on Earth is formed based on previous experience. Impact events represent some of the most destructive phenomena that have ever occurred on Earth. These events occur when large celestial bodies, such as asteroids or comets, collide with our planet. Such collisions do not merely leave craters, they instantaneously alter the entire ecosystem, triggering global catastrophes that can lead to mass extinctions. For instance, an impact from a body with a diameter of about 10 kilometers releases energy equivalent to tens of millions of atomic bombs. This impact creates immense waves of heat and pressure that can incinerate all life within a radius of hundreds of kilometers. Moreover, the ejection of dust and gas into the atmosphere blocks sunlight, causing a sharp drop in global temperature. This phenomenon, known as nuclear winter, worsens living conditions because photosynthesis stops and the food chain collapses. Research indicates that some of the most well-known extinctions, such as the disappearance of dinosaurs, were caused by such catastrophic events. Scientists, for example, hypothesize that the impact leading to the extinction of dinosaurs caused global ecosystem changes that lasted for millions of years. As a result of this event, along with climate change, there were also significant changes in the biogeochemical composition of the atmosphere and oceans. Impact events underscore the fragility of our planetary equilibrium. Even small changes in the orbits of asteroids can lead to catastrophic consequences for life on Earth. A collision with a celestial body serves as a reminder of how dependent we are on the stability of conditions on our planet. Throughout Earth's history, more than 200 major impacts have been recorded, and although most did not result in such extensive consequences as the extinction of dinosaurs, they all left their mark on geological history. Each impact leaves a crater that can serve as a reminder of how fragile life on the planet can be and how quickly it can change under the influence of celestial forces. Scientific research shows that in the last million years, Earth has collided with large asteroids approximately every 100,000 years, highlighting the likelihood that we may encounter similar events in the future. Considering the speed at which these bodies can move and the power of their impacts, it is important to understand that such events shape not only the geological, but also the biological history of our planet. For example, craters formed as a result of impacts can serve not only as geological monuments, but also as places where scientists study the consequences of collisions. These studies help us better understand how life on Earth adapted to changes and how the planet recovered after catastrophes. Collisions with celestial bodies remind us that we are just a small part of a vast and ever-changing system, where every event has significance. When a celestial body such as an asteroid or meteor enters Earth's atmosphere, it encounters numerous physical phenomena. At speeds reaching several tens of kilometers per second, atmospheric resistance causes the body's surface to heat up rapidly, resulting in a bright light and the formation of a luminous trail known as a bolide. This heating process occurs in just a few seconds, and at an altitude of around 100 kilometers, the meteor can break apart due to intense friction with the atmosphere. This process releases a tremendous amount of energy, equivalent to the explosion of several tons of TNT. Upon reaching Earth's surface, the meteor collides with it, releasing colossal energy that can amount to billions of joules. This results in the formation of a shockwave that spreads in all directions, causing significant damage over a large area from the impact site. The shockwave compresses the air, creating a sharp pressure gradient that can lead to the formation of a sound boom audible over long distances. The collision also releases a vast amount of heat, causing the surrounding materials to melt. As a result, a crater is formed, which has a characteristic funnel-shaped appearance. The central uplift of the crater is formed due to the reverse movement of the molten material, which is ejected from the crater and then falls back, creating a mound in the center. This process can take only a few seconds, but the consequences can be global. Seismic waves generated by the impact spread across the planet, causing earthquakes and even tsunamis if the impact occurs in the ocean. For example, the impact that occurred in Chicxulub, Mexico, approximately 66 million years ago, not only caused mass extinction of dinosaurs, but also led to global climate changes. The diameter of the crater is approximately 120 kilometers, and its formation released millions of tons of dust and gas into the atmosphere, resulting in prolonged cold spells and then acid rain. Impact craters like the Tunguska crater in Siberia demonstrate how the energy of the impact can damage ecosystems over large areas. Shock waves can cause devastating effects on buildings and natural landscapes, creating impressive geological formations that are studied by scientists worldwide. The Chicxulub crater, located on the Yucatan Peninsula in Mexico, has a diameter of approximately 180 kilometers and is considered one of the most significant geological formations on Earth. Its age is estimated to be around 65 million years, coinciding with the period of mass extinction that led to the disappearance of about 70% of all living species on the planet, including dinosaurs. Scientists believe that this crater was formed as a result of the impact of an asteroid with a diameter of about 10 kilometers, which struck Earth with an energy equivalent to 1 billion atomic bombs dropped on Hiroshima. This impact not only caused an immediate catastrophe, but also triggered numerous secondary effects, such as global fires, dust, and gas emissions that blocked out the sun for an extended period. The resulting crater served as a window into the past, allowing researchers to delve into events that altered the course of evolution. Surrounding the crater are unique geological formations that formed due to subsequent erosion, making this region a true laboratory for studying processes that occurred on Earth after the impact. On the surface of the crater, remnants of ancient seas and forests can be observed, preserved as fossils, which testify to the rapid changes in ecosystems. Incidentally, the crater was discovered in 1968 when Mexican geologists studying geological anomalies stumbled upon this remarkable trace of cosmic intervention in our history. In recent decades, scientists like Dr. Alan Hildebrand have actively studied the crater using geophysics and geochemistry methods to understand how this catastrophe occurred and what consequences it had for life on Earth. Additionally, the crater has become a popular destination for tourists and researchers eager to visit the site where the cosmos directly intervened in the history of our planet. Research has yielded unique data on the composition of rocks and minerals, providing insights into the conditions that led to global climate and ecosystem changes. Experts believe that studying the Chicxulub crater not only helps unravel the mysteries of the past, but also allows us to predict the possible consequences of future impacts. In this context, the crater is more than just a geological formation. It is a symbol of the fragility of life on Earth, a reminder of how vulnerable our planet is to cosmic threats. The Chicxulub crater, with its impressive history and scale, continues to be a subject of intense scrutiny by scientists who strive to unravel its secrets and understand how a single catastrophe can alter the fate of entire species. An asteroid that created the Chicxulub crater had a diameter of about 10 kilometers and was traveling at a speed of approximately 60,000 kilometers per hour. This collision occurred around 66 million years ago and was one of the most catastrophic events in the history of our planet. The energy released during the impact was estimated to be equivalent to 10 billion atomic bombs, comparable to the one dropped on Hiroshima, which resulted in the formation of a crater with a diameter of about 130 kilometers. At the moment of impact, a flash of light was produced, its brightness exceeding that of the sun, illuminating the surroundings for hundreds of kilometers. As a result of this colossal energy, the material was instantly vaporized, forming a cloud of hot gases and particles that rose to tens of kilometers in the atmosphere. In the first minutes after the impact, the material ejected reached such heights that some particles even escaped into space. This led to global consequences, including climate change that affected the entire planet. Around 30% of the biomass was destroyed, and life on Earth was fundamentally altered. The cloud of dust and gas formed blocked out the sunlight, causing a sharp drop in temperature on the planet for several years, creating conditions unsuitable for the survival of many species. This event was one of the main causes of the mass extinction, leading to the disappearance of dinosaurs, who had ruled the planet for over 100 million years. The impact was so powerful that the formed crater became a significant object of study not only for geologists, but also for paleontologists seeking to understand how such catastrophes affect the evolution of life. Astronomers and physicists continue to investigate the consequences of this collision to better understand the mechanisms behind such events and their impact on climate and ecosystems. After the Chicxulub impact, the world was plunged into genuine chaos. A fiery storm resulting from the collision engulfed territories within thousands of kilometers of the crater. Temperatures reached several thousand degrees Celsius, incinerating vegetation and animals in mere minutes. Ash and debris, ejected into the atmosphere, caused instantaneous darkness, making sunlight inaccessible to ecosystems that had evolved over millions of years. This was not just any ordinary day. It was an apocalypse. Tsunamis, formed due to the impact's force, crashed onto coastlines, raising waves up to 100 meters high and sweeping away everything in their path. They decimated coastal ecosystems that were home to numerous species, including marine reptiles and ammonites. Earthquakes, triggered by the impact on the Earth's crust, were felt even thousands of kilometers from the impact site. Scientific research indicates that the magnitude of these earthquakes could reach 9 on the Richter scale, leading to the destruction of mountain ranges and the alteration of river courses. In the aftermath, acid rains began to fall, formed from chemical compounds released into the atmosphere. The acidity of these rains was so high that they could erode the Earth's surface and cause plant death, depriving animals of food sources. Animals that did not perish immediately became victims of food and oxygen shortages. Scientists calculated that within just a few hours after the impact, the global ecosystem began to collapse, and many species, including dinosaurs, were on the brink of extinction. As a result of this catastrophe, which occurred approximately 65 million years ago, around 75% of all species on the planet went extinct. These events served as a catalyst for changes that led to a new phase in the evolution of life on Earth. The Chicxulub crater, which has persisted to this day, serves as a reminder of how quickly and irreversibly the world can change. After the impact of asteroid fragments in Chicxulub, a so-called impact winter descended upon the planet, lasting from several months to several years. Dust and debris managed to obscure the sun, leading to a sharp drop in Earth's temperature. Studies indicate that the average temperature could have fallen by 10 to 12 degrees Celsius, with some regions experiencing drops of up to 20 degrees. This global cooling effectively halted photosynthesis. Plants, which were the foundation of food chains, began to die off, affecting all animals that depended on them. Leading paleontologists like D.J. Pale and E.M. Copy assert that survival became a matter of chance even for the most resilient species. Around 75% of all species on Earth went extinct, including not just dinosaurs, but many mammals, birds, and marine creatures. For example, fossil records show that marine reptiles like plesiosaurs disappeared during this period. Since plants could no longer produce oxygen and animals could not find food, ecosystems began to collapse. The rates of extinction were unprecedented. Numerous changes occurred in the biosphere over several million years following the impact. Scientific research confirms that many ecosystems did not recover for millions of years. Meanwhile, as the impact winter ended, Earth faced new climatic conditions, including increased humidity and acidic rain, which also contributed to the extinction. For instance, in some places, vast swamps formed, becoming homes for new species, but the old ecosystems could not recover. Threats posed by the changing climate only intensified. Scientific data showed that the level of carbon dioxide significantly increased, also affecting climatic conditions. Studies indicate that such climatic changes took millions of years to subside before ecosystems began to adapt to the new conditions. There is evidence that new species, such as early mammals, emerged during this time, capable of adapting to harsh conditions. Thus, the Chicxulub impact not only caused catastrophic extinction, but also served as a catalyst for new evolutionary stages in life on Earth, shaping the future of ecosystems. As a result, by the end of the Cretaceous period, new species had already emerged that became the basis for modern ecosystems. Paleontologists note that it was after these events that mammals began to dominate, which in turn laid the foundation for the further evolution of life on Earth. The Chicxulub impact, which occurred approximately 65 million years ago, was a catastrophic blow for the dinosaurs, who had ruled the planet for over 150 million years. These impressive creatures, from small velociraptors to giant tyrannosaurs, were unable to adapt to the sudden changes in ecosystems. The asteroid impact created powerful waves that destroyed coastal lines, followed by massive forest fires that covered vast areas, killing vegetation that dinosaurs relied on for food. In the atmosphere, clouds of dust and soot rose, leading to a global cooling event known as the nuclear winter. Temperatures dropped by 10 degrees Celsius, making life unbearable for heat-loving dinosaurs. Studies show that as a result of this cold, ecosystems once teeming with life began to collapse, leading to the extinction of more than 90% of all species on the planet. Paleontologists like Dr. David Pohl and his team, analyzing fossil remains, concluded that many dinosaur species were unable to adapt to the new conditions. For example, herbivorous dinosaurs like Triceratops and Brontosaurus, due to their large size, required a lot of food, and with the disappearance of vegetation, their chances of survival dropped sharply. Predators like Allosaurus and Tyrannosaurus were left without prey, leading to their rapid extinction. While some species went extinct, others, such as the ancestors of modern birds, found ways to survive, indicating that some animal groups were able to adapt, but this did not apply to dinosaurs, which were unable to cope. Ultimately, this era ended, and the once mighty creatures, once thought to be invincible, disappeared from the face of the Earth, making way for new forms of life. Studies show that within a few million years after the impact, mammals began to develop and occupy the ecological niches left by dinosaurs. The period known as the Cenozoic became the foundation for the appearance of new species, among which mammals dominated, not reptiles. For instance, the first primates began to appear around 60 million years ago, ultimately leading to the evolution of humans. The Chicxulub impact was not just the end of the dinosaur era, it opened a new chapter in the history of life on Earth. After the Cretaceous-Paleogene extinction event, which occurred around 66 million years ago, only small mammals, birds, crocodiles, and turtles remained on the planet. These groups of animals were able to adapt to the new conditions, which allowed them to survive in the changed world. Small mammals, such as the first rodents and insectivores, had several important advantages. They were small, which allowed them to hide from predators and find shelter in burrows or under tree roots. Their high reproductive capabilities contributed to the rapid recovery of populations. For example, according to paleontologists, the number of mammal species increased several times during this period, leading to the radiation of these animals. Birds, which evolved from theropods, gained the ability to move freely through the air, which gave them access to new food sources and nesting sites. Some of them evolved into larger forms, such as penguins and eagles, which occupied specific ecological niches previously inaccessible to other animals. Crocodiles, which survived due to their ability to adapt to both aquatic and terrestrial environments, were able to use their powerful jaws and armor to protect themselves and hunt. They inhabited various ecosystems, from freshwater bodies to coastal areas. Turtles, which possessed a unique protective shell, adapted to various conditions, including life in water and on land. Their slow metabolism and ability to store energy allowed them to survive in conditions of food scarcity. As a result of these adaptations, by the end of the Paleocene, which was approximately 10 million years after the catastrophe, mammals began to actively fill the ecological niches left by the dinosaurs, and their diversity began to increase. For example, by this time the first primates appeared, which was an important step in the evolution of mammals. The survival of these groups of animals demonstrated their ability to adapt to changing ecosystems, which later led to the formation of new species and entire ecosystems. In the Paleocene, around 60 million years ago, there were already more than 100 species of mammals, whereas in previous epochs, their number was significantly smaller. Supervolcanoes are among the most powerful and destructive geological formations on Earth. They differ from ordinary volcanoes in their colossal scale and ability to eject vast quantities of magma and ash into the atmosphere. Unlike traditional volcanoes, which can erupt up to several cubic kilometers of material, supervolcanoes can expel hundreds to thousands of cubic kilometers of magma in a single eruption. For instance, an eruption of a supervolcano can create a caldera, a massive depression formed by the collapse of a volcanic mountain following a powerful eruption. These calderas can reach diameters of tens of kilometers, making them easily visible from space. Supervolcanoes form as a result of the accumulation of enormous volumes of magma in underground reservoirs, when the pressure inside these reservoirs reaches critical levels. This pressure can cause magma to burst to the surface, triggering catastrophic eruptions that can have global consequences. For example, such eruptions can release enormous quantities of aerosols and ash into the atmosphere, blocking sunlight and causing rapid temperature fluctuations on Earth. This can lead to so-called volcanic winters, where the planet's climate changes for many years, causing global disruptions in agriculture and ecosystems. There is evidence that such events have occurred in the past, such as the eruption of the Toba supervolcano approximately 70,000 years ago. This eruption likely led to a significant reduction in human population, causing a global climate crisis. Research indicates that supervolcanoes can remain in a state of active dormancy for thousands of years, and their potential threat remains relevant even today. Therefore, supervolcanoes are not just geological formations, but powerful systems capable of influencing the climate and life on the planet on a scale that is difficult to overestimate. The average size of a supervolcano reservoir can reach tens of kilometers in depth, and its magma can contain unique chemical elements that affect the composition of the atmosphere. It is important to note that such powerful eruptions are not frequent, but their consequences can be catastrophic, affecting not only local ecosystems, but entire continents. For example, researchers from the University of California have calculated that an eruption of a supervolcano could release up to 300 million tons of carbon dioxide into the atmosphere, exacerbating the greenhouse effect and influencing climate conditions for many years to come. Supervolcanoes attract the attention not only of geologists, but also of climatologists, as their study can help understand the potential consequences of such catastrophic events in the future. Yellowstone caldera is one of the most impressive geological formations on the planet, formed as a result of a series of catastrophic eruptions of a supervolcano that followed the last eruption approximately 600,000 years ago. The dimensions of this caldera are colossal. Its diameter reaches about 30 kilometers, comparable to the size of a large city. In the center of the caldera, there are numerous hot springs, geysers, and thermal pools that create a unique landscape. But beneath this picturesque surface lies a powerful reservoir of magma capable of triggering one of the most destructive eruptions in history. The structure of the caldera is complex. It consists of multiple layers of volcanic rocks formed by repeated eruptions, leaving behind vast fields of solidified lava and tuff. Scientific research indicates that beneath the caldera lies a massive magma body occupying a volume of around 600 cubic kilometers, making it one of the largest volcanic reservoirs in the world. The sense of hidden power beneath the picturesque landscape of Yellowstone can be felt when observing geysers, such as the Old Faithful, which shoots streams of hot water up to 30 meters high. This is just a small demonstration of the power lying deep beneath the earth. Data collected through seismic and acoustic studies show that the caldera is in a state of active monitoring, and scientists are recording constant changes in its geological structure. For example, in recent years, there have been observed uplifts and subsidences of the surface, indicating the movement of magma beneath the caldera, which confirms its activity. Research shows that over the past few decades, the temperature in some hot springs has risen by several degrees, which may also indicate instability in the underground magma systems. This power, hidden beneath the Earth's crust, makes Yellowstone not only an object of scientific research, but also a symbol of the power of nature, capable of reminding us of its presence at any moment. In addition, the caldera is home to a unique ecosystem where rare species such as bison and wolves have adapted to life in the conditions of active volcanism. Thus, the Yellowstone caldera is not just a geological formation, but a whole system of great importance for understanding volcanic activity and its impact on the surrounding environment. Scientific observations and research conducted in this region continue to deepen our knowledge of how supervolcanoes can affect the climate and ecosystems on Earth. In this context, it is worth noting that Yellowstone is also a UNESCO World Heritage Site, highlighting its cultural and natural value. The last major eruption of Yellowstone occurred approximately 600,000 years ago and was one of the most powerful volcanic events in Earth's history. This eruption resulted in the formation of a caldera covering an area of around 3,000 square kilometers. During the eruption, more than 1,000 cubic kilometers of volcanic material, including ash, lava, and gas, were released into the atmosphere. The ash spread thousands of kilometers from the volcano, reaching both the eastern coast of the United States and parts of Canada. Scientific research indicates that the ash fell over an area extending up to 800 kilometers from the eruption site, causing significant problems for the ecosystem and climate of the region. The sky over North America was shrouded in a dark cloud of ash for several months, significantly reducing the amount of sunlight reaching the surface. This phenomenon, known as a volcanic winter, led to a sharp drop in temperature, which could have decreased by 10 degrees Celsius or more. Vegetation began to wither under the layer of volcanic material, and many species of animals faced the threat of extinction due to changes in their natural habitat. Some studies suggest that this eruption could have had long-term effects on the climate, causing changes in atmospheric conditions and ecosystems. For example, changes in temperature and rainfall could have led to the disappearance of certain plant species, which in turn affected food chains. Ash deposited on the soil could have altered its chemical composition, also negatively impacting agriculture. Although people at the time could not observe the consequences of this catastrophic eruption, archaeological findings show that even after tens of thousands of years, the ecosystem had not fully recovered. Ash that entered rivers and lakes also altered their chemical parameters, affecting the composition of water bodies and the species living in them. The volcanic activity of Yellowstone continues to be a subject of active research, and scientists are studying how such events could impact the future of humanity. Over time, evidence has been found that such eruptions can recur with a periodicity of several 100,000 years, necessitating preparations for potential catastrophes. This makes Yellowstone not only an object of study, but also a significant indicator of the risks associated with volcanic activity. The caldera and its surroundings continue to attract the attention of scientists and tourists who want to see the consequences of one of nature's most destructive forces. Studying the aftermath of this eruption provides insights into how ecosystems recover from catastrophes and what measures can be taken to protect the environment. Scientific data show that even tens of thousands of years after the eruption, its effects are still felt in the region's ecosystem. Supervolcano Toba on Sumatra is one of the largest volcanoes on the planet, with a caldera that reaches approximately 100 kilometers in diameter. This gigantic formation emerged as a result of an eruption that occurred around 78,000 years ago, when the volcano spewed more than 30 cubic kilometers of magma and ash into the atmosphere. It is considered one of the most powerful eruptions in Earth's history, with its consequences felt worldwide, including a sharp drop in temperature and climate change, which, according to some researchers, could have led to a significant reduction in human and other species populations. At the center of the caldera lies Lake Toba, which covers around 1,600 square kilometers and reaches a depth of up to 500 meters. This lake, surrounded by picturesque landscapes, creates a contrast between the serene beauty and the potential destructive power hidden beneath its waters. Small islands, such as Supang, can often be seen on the lake's surface, adding to its charm. Surrounding the lake are mountain ranges covered in green forests, creating ideal conditions for diverse flora and fauna. Geological data indicate that Toba's volcanic activity was not limited to a single catastrophic eruption. In the past 1,000 years, there have been more minor eruptions that have also left their mark on the landscape. These events allow scientists to study processes occurring within the Earth's crust and gain insight into the mechanisms that could lead to such massive catastrophes in the future. One interesting fact is that numerous hot springs are located near Toba, indicating ongoing volcanic activity. Studies conducted by local and international scientists have shown that there is a large magma chamber beneath Lake Toba, which could one day trigger a powerful eruption. This poses a constant threat to the local population and the ecosystem as a whole, but also attracts tourists eager to witness this unique natural phenomenon. Scientific research continues, and each new project brings additional data on Toba's structure and activity. The volcano is a significant object of study not only for volcanology, but also for ecology, as its impact on the surrounding environment, as history shows, was substantial. The recovery of ecosystems after Toba's eruptions is studied by scientists worldwide, helping to understand how nature adapts and recovers from catastrophes. The eruption of the Toba volcano, which occurred approximately 74,000 years ago, was one of the most powerful volcanic events in Earth's history. This catastrophic event released enormous volumes of ash and gases into the atmosphere, leading to significant climate deterioration on the planet. Studies indicate that during the eruption, the volcano expelled at least 1,000 cubic meters of ash, equivalent to several hundred modern nuclear bombs. As a result of this release, the sky over extensive territories on Earth darkened for years, and the sun became virtually invisible. Scientists hypothesize that this phenomenon could have triggered a sudden cooling period known as the volcanic winter, which led to a global temperature drop of several degrees Celsius over an extended period. This cooling, in turn, had a devastating impact on agriculture and ecosystems, resulting in significant losses among early human populations. Estimates of human population numbers at the time vary, but some research suggests that the population may have declined to a few thousand individuals, putting the survival of the Homo sapiens species at risk. A crucial aspect of this event is its impact on the genetic structure of modern humanity. DNA analysis shows that many people today share common ancestors who survived this catastrophic eruption. Around 99% of all human genes, according to researchers, originated from those few who endured extreme stress and resource scarcity. Archaeological findings, such as stone tools made around this time, reveal changes in human behavior and migration patterns, indicating how they adapted to new conditions. The long-term consequences of the Toba eruption continued to be felt for centuries, shaping ecosystems and migration routes that ultimately contributed to the development of various civilizations. This event not only altered the climate, but also left an indelible mark on human history, becoming a significant factor in the evolution of our species. The ongoing volcanic activity of Toba makes it a subject of study for scientists investigating the impact of catastrophes on biological diversity and climate conditions. Volcanic activity significantly influences Earth's climate, and this impact manifests through complex interaction mechanisms involving the release of gases and aerosols into the atmosphere. When volcanoes erupt, they emit massive amounts of carbon dioxide, sulfur dioxide, and other greenhouse gases that can alter the planet's thermal balance. For instance, carbon dioxide traps heat in the atmosphere, potentially leading to temperature increases. However, simultaneously, aerosols such as sulfur and ash, with their reflective properties, can block solar radiation. This results in a decrease in the amount of sunlight reaching Earth's surface, and consequently, a drop in temperature. The intricate system in which these processes interact creates a dynamic picture where short-term temperature changes can coexist with long-term trends caused by the accumulation of greenhouse gases. Volcanic aerosols can remain in the atmosphere for several days to several years, depending on their height and type of eruption. For example, aerosols released at heights above 10 kilometers can spread globally, affecting climate conditions in distant regions. They can cause phenomena such as volcanic winter, where global temperature drops by several degrees, impacting agriculture and ecosystems. The effects of such emissions on climate can be illustrated by the fact that significant eruptions are followed by changes in precipitation and the amount of sunlight reaching the surface within a year. Volcanic activity can also affect the ozone level in the stratosphere, where sulfur emissions can lead to the formation of sulfuric acid droplets that redistribute solar radiation and can either increase or decrease the level of ultraviolet radiation reaching the surface. This interaction between volcanoes and climate demonstrates how internal Earth processes can influence atmospheric conditions, shaping long-term climate changes that can have significant consequences for life on the planet. Understanding these mechanisms is crucial for predicting and adapting to future climate changes. Volcanic activity is not just a phenomenon, it is a complex network of interconnections where each action has its consequences. Such research helps scientists better understand how natural disasters can alter the climate and how this, in turn, affects life on Earth. One example is the study of volcanic activity over the past 2 millennia, during which scientists have recorded changes in temperature and precipitation, correlating them with historical data on eruptions. In the year 1816, the world encountered an unusual climatic phenomenon known as the Year Without a Summer. This event was a consequence of one of the most devastating volcanic eruptions in history, the eruption of Tambora on the Indonesian island of Sumbawa, which occurred in April 1815. The volcano released massive amounts of ash and sulfur gases into the atmosphere, leading to a significant drop in global temperatures. The summer of 1816, instead of the usual heat, was cold and rainy. In some regions of Europe, such as Germany and Britain, temperatures in June and July dropped by 10 degrees Celsius compared to the norm. Snow fell in June, which was an absolute anomaly for these latitudes. People watched with concern, not understanding that these strange phenomena were caused by volcanic activity in distant Indonesia. As a result of the unusually cold summer, agriculture suffered, and the grain harvest in Europe decreased by 35%. Farmers, unprepared for such climatic changes, faced food shortages. In some regions, such as New England in the United States, snow and frost prevented even the planting of summer crops, leading to widespread crop failures. Additionally, heavy rains destroyed whatever little could be grown. People suffered from hunger, leading to social unrest and migration. For example, in 1817 in the United States, people began to move in search of a better life, not only due to economic hardships, but also due to the climate catastrophe. In Europe, there were riots against high bread prices, which became scarce. At this time, artists and writers such as Lord Byron and Mary Shelley described the atmosphere of anxiety and uncertainty that enveloped society. Byron, while in Switzerland, wrote a poem reflecting the gloomy mood of his time. people began to question the future, wondering how climate changes could affect their lives and well-being. Scientific explanations were not yet widespread, and many sought mystical causes for the events. While some tried to adapt to the new conditions, others fell into despair, believing it to be a harbinger of the end of the world. Later, scientific research showed that the eruption of Tambora led to global climate changes caused by the release of sulfur gases that blocked sunlight. This confirms that nature can at any moment confuse humanity, causing it to be lost in conjectures and fears. As a result, people around the world faced consequences that changed their accustomed way of life and left a deep mark on history. The mortality rate from hunger in some regions of Europe reached 10%. The eruption of the Tambora volcano in 1815 not only caused climate changes, but also profound shifts in the cultural life of Europe, reflected in literature and art of the period. In 1812, Mary Shelley wrote her famous novel Frankenstein, inspired by the atmosphere of the time when darkness and cold enveloped the continent. She created the image of a creature rejected by society, symbolizing the fears and uncertainties that arose from the natural catastrophe. The plot of the novel is permeated with themes of solitude and destruction, which became particularly relevant in the context of the year without a summer. Artists also reacted to these changes, creating gloomy landscapes that reflected apocalyptic moods. For example, in 1816, the English painter John Constable created the painting The Vale of Sloe, where dark clouds and gray light create an atmosphere of despair. Around the same time, the Italian painter Giuseppe Malo created a series of paintings where nature is depicted as a threat, emphasizing the fragility of human existence. These works became a reflection of the fear of the future that prevailed in society and showed how natural catastrophes affected people's psychology. Literature of this time was also filled with dark themes and warnings, such as in the poetry of Lord Byron and Percy Bysshe Shelley, who raised questions about humanity and its place in the world. Lord Byron often addressed the tragic consequences of human activity in his poems, while Percy Shelley sought ways to harmonize with nature, which was particularly relevant in the context of climate changes. These authors used nature as a metaphor to describe internal conflicts and social problems. In the 1820s, more and more writers began to use images of destructive elements to convey the fears and experiences of their time. For example, in Walter Scott's novel The Pirate, dark landscapes and stormy seas serve as a backdrop for the tragedies that befall the characters. These works not only reflected reality, but also shaped public opinion, contributing to the awareness of the dangers associated with climate change. The cultural impact of The Year Without a Summer was not limited to literature and painting, but also extended to music. Composers of the time, such as Ludwig van Beethoven, created works with gloomy and anxious motifs that reflected the general state of society. For example, his Symphony No. 7, written in 1812, is filled with drama, which can be attributed to the influence of climate changes and social unrest. These cultural responses to natural catastrophes not only preserved the fears and hopes of people, but also became the basis for classical works that remain relevant today. In the end, The Year Without a Summer became not just a climatic event, but also a catalyst for cultural changes, leading to the creation of works that discuss questions about humanity and its place in the world. 8 years after these events, in 1820, the novel Frankenstein was first published, and it has continued to generate interest and discussion, becoming a classic of world literature. Glacial periods are phases in the history of Earth when vast masses of ice covered significant portions of continental territories. These cycles of advance and retreat of glaciers occur over millions of years, and their impact on the planet is hard to overestimate. Glaciers, reaching thicknesses of up to 3 kilometers, can transform landscapes, altering river systems, and forming new geographical features. As a glacier moves, it carves out valleys, creates fjords, and leaves behind characteristic moraines that become true monuments of the glacial age. The process of glacier formation begins with the accumulation of snow, which over time turns into ice under pressure. This ice gradually starts to move under its own weight, leading to its stretching and fracturing. Glaciers can move at speeds ranging from several centimeters to several meters per day, creating the impression of slow but inexorable progress. As a result of this movement, erosion of rocks occurs, which are subjected to the weight of the ice, and debris is transported over long distances. When a glacier retreats, it leaves behind altered landscapes, such as lakes formed in depressions where the ice once stood. These glacial lakes, such as Lake Michigan, often become important ecosystems and sources of fresh water. Over time, due to repeated cycles, glaciers can change even the climatic conditions in surrounding regions, leading to changes in vegetation and animal life. It is important to note that glacial periods are not isolated events, but part of broader climatic changes associated with variations in Earth's orbit and solar activity. These changes occur within cycles known as Milankovitch cycles, which affect the distribution of solar light on Earth's surface, thereby causing global climatic changes that can last for tens of thousands of years. Throughout their existence, glaciers have covered up to 30% of Earth's surface, and their influence can still be observed in the modern world. For example, in the Alps, which were heavily affected by glacial processes, one can find traces of these ancient glaciers in the form of deep valleys and sharp peaks that have become symbols of the mountain landscape. Glacial periods continue to leave their mark on Earth's geological history, demonstrating how even slow and unassuming processes can significantly alter the planet's appearance. Currently, despite global warming and the retreat of glaciers, scientists continue to study these processes to better understand their impact on climatic changes and ecosystems. Glaciers, despite appearing stationary, are active participants in geological processes, capable of causing significant changes in the surrounding environment. Each glacial period leaves behind unique geological monuments that become objects of study for geologists and climatologists. Approximately 20,000 years ago, during the last glacial maximum, vast areas of northern continents were covered by a multi-kilometer layer of ice. This glaciation affected not only modern Canada and the northern parts of the United States, but also the northern regions of Europe and Asia. The ice sheet, stretching thousands of kilometers, altered not only the landscape, but also the climate conditions. The sea level at that time was about 120 meters lower than today, opening up new lands such as the Bering Land Bridge, which connected Asia with North America. These changes facilitated the migration of people and animals seeking new territories to live in. At that time, the climate in the central parts of Europe and Asia was significantly colder and drier than today, contributing to the formation of extensive tundras and steppes inhabited by unique fauna of the glacial period. Here, mammoths, woolly rhinos, bison, giant ground sloths, and saber-toothed tigers lived. Mammoths, reaching up to 4 meters in height with large curved tusks, became a symbol of this period. They grazed on vast grassy plains where special plant species adapted to the cold climate grew. These animals preferred open spaces where they could find food, while more heat-loving species retreated to the south. On the southern edges of the glaciation, the climate was milder, allowing other animal species and possibly even early humans to survive, utilizing resources for their survival. Glacial conditions also contributed to the formation of specific ecosystems where the interaction between species occurred under challenging conditions. In these conditions, Paleolithic people used stone tools for hunting large game, and their way of life was directly tied to changes in the surrounding environment. The glacial period laid the foundation for the formation of modern ecosystems, and its influence is still felt today in the form of unique characteristics of fauna and flora. Around 10,000 years ago, with the end of the last glacial maximum, a process of global warming began, leading to the melting of glaciers and the return of the sea level to its current levels, which changed the landscape and biodynamics of the region. In the last tens of thousands of years during the Ice Age, Earth was home to a unique megafauna, which included giants such as mammoths, woolly rhinos, cave bears, and saber-toothed cats. For example, mammoths could reach heights of up to 4 meters at the shoulder and weigh around 6 tons. These massive herbivores had thick fur that protected them from the harsh cold. They inhabited the tundras and steppes of Eurasia and North America, feeding on grasses and shrubs, and played a crucial role in the ecosystem, maintaining the balance between plants and other animal species. Woolly rhinos, with their powerful horns up to 1 meter long, also lived in these conditions, foraging for food under the snow cover. Their strong limbs allowed them to navigate complex, icy landscapes. Cave bears, growing up to 3 meters in length and weighing up to 1 ton, lived in caves and, as evidenced by finds, were omnivorous, which helped them survive in conditions of food scarcity during the winter. These bears could hibernate for up to 7 months, allowing them to adapt to extreme climatic conditions. Saber-toothed cats, known for their distinctive dental structure, hunted large herbivores like mammoths and rhinos. These predators could reach lengths of up to 2 meters, and their hunting skills allowed them to successfully compete with other predators of the time. Saber-toothed cats were characterized by a tactical hunting style, involving stealthy approaches and sudden attacks. The megafauna of that time played a key role in maintaining the ecosystem, shaping the landscape and facilitating the spread of seeds. The disappearance of these animals at the end of the last ice age around 10,000 years ago was a catastrophe for the ecosystem, altering the natural course of life on the planet. Research shows that climate change and human hunting played a key role in their extinction. Scientific excavations in Siberia, in particular, have provided numerous remains of mammoths and other megafauna representatives, which are now housed in museums around the world, allowing us to learn more about the life and ecology of that time. Findings such as fossils, footprints, and even preserved fur fragments help recreate the picture of that harsh but full of life world, where giant herbivores and their predators coexisted in a complex network of interdependencies. At the end of the Pleistocene, about 15,000 years ago, a massive thawing of glaciers began, freeing up vast territories from the ice cover that had previously stretched from Scandinavia to North America. This event not only altered the landscape, but also served as a catalyst for the formation of new ecosystems. As the glaciers retreated, they left behind enormous areas that gradually filled with water, creating numerous lakes such as Lake Michigan and Lake Superior. These bodies of water became homes for diverse ecosystems, where new plant and animal species adapted to the changing conditions. Scientific research indicates that the global sea level began to rise, reaching its maximum around 8,000 years ago, when it was 10 meters higher than today. This process strengthened the existence of rivers like the St. Lawrence River, which began to flow with new vigor, forming new river systems. With the retreat of the ice, tundra and taiga began to change, and forests gradually moved northward. Scientific data shows that forests of pine and birch trees began to populate previously barren areas where only mosses and lichens had grown. Studies conducted by scientists from the University of California reveal that by the end of the Holocene, around 6,000 years ago, forests had reached the latitude where cities like Arkhangelsk are now located. This created new ecosystems where predators and herbivores began to coexist in conditions that were vastly different from those of the glacial period. For example, forest reindeer and lynx began to migrate northward, following the vegetation, while more heat-loving species like roe deer and moose also began to occupy new habitats. The appearance of species, such as the squirrel and the woodpecker, which colonized the forests that replaced the tundra, serves as an example of adaptation to new conditions. Thus, climate change and the retreat of glaciers became the primary factors determining the development of the biosphere of the region. Scientific research conducted in recent decades has shown that these changes led to a significant increase in biodiversity, as evidenced by fossil finds and paleobotanical analyses. With each stage of the retreat of the ice, new animal and plant species found their niche in the ecosystems, creating unique communities that continue to exist and develop to this day. Melting of glaciers at the end of the last ice age led to catastrophic floods that transformed the landscapes of entire regions. One striking example of such events is the breaching of glacial lakes, when massive amounts of water, accumulated in natural reservoirs, suddenly burst forth. In such cases, the water bursting from the lakes could erode multi-meter layers of rock in just a few hours, creating new canyons and valleys. For instance, in the area of Lake Missoula, located in the modern states of Montana and Washington, several powerful breaches occurred around 14,000 years ago. These floods, known as the Missoula floods, resulted in the formation of canyons and terraces that can still be seen today as impressive geological formations. The discharge of water from the lake could reach such magnitudes that it created powerful streams capable of washing away everything in their path. For example, as a result of one such flood, when an ice dam could no longer withstand the pressure, approximately 13 cubic kilometers of water burst from the lake in just a few days, forming a unique scabland topography. This term describes complex geomorphological structures formed during catastrophic floods, including boulders, sedimentary rocks, and eroded patches, which testify to the immense power of the water. A notable example is the Columbia River, into which vast amounts of water were discharged, creating powerful waterfalls and cliffs that still awe with their grandeur. As a result of these catastrophic events, the landscape of the region was transformed beyond recognition, giving rise to unique geological formations, such as rocks formed by erosion and new valleys that were created in just a few weeks. The breaching of glacial lakes not only altered the geography, but also created new ecosystems that, in turn, led to a diversity of flora and fauna. These floods also posed a threat to many ancient human settlements, forcing them to seek new places to live. The study of such floods allows geologists to reconstruct ancient climatic conditions and the dynamics of glaciers, which undoubtedly enriches our understanding of the geological history of Earth. The breaches of glacial lakes left behind traces that are still being studied and analyzed, and continue to serve as an important source of information about how climate changes affect the planet. The study of these catastrophic floods is key to understanding not only the past, but also to predicting future changes in the climate. At the end of the Pleistocene epoch, around 11,000 years ago, a mass extinction of megafauna occurred, affecting numerous large mammalian species such as mammoths, mastodons, giant sloths, and saber-toothed tigers. Mammoths, reaching heights of up to 4 meters and possessing long, curved tusks, inhabited vast steppes of Eurasia and North America. Meanwhile, mastodons, with their characteristic tusks and smaller size, inhabited forests and grasslands. One of the largest mammals of that period was the giant sloth, weighing up to 4 tons and distinguished by its powerful limbs. Scientists suggest that climatic changes, brought about by the end of the last ice age, played a key role in this extinction. Temperatures began to rise, and ice sheets retreated, leading to changes in ecosystems and the loss of familiar habitats. However, it is also important to consider the impact of humans, who began to actively hunt these large animals. Archaeological finds, such as mammoth remains with signs of human tools, confirm that hunting was a widespread practice among ancient people. In particular, data collected by archaeologists from the University of California shows that hunters used stone tools to butcher animal carcasses, indicating that they could significantly influence megafauna populations. Moreover, hunting mammoths and other large animals was not only a means of survival, but also an important part of social interaction in early human communities. Research shows that megafauna played a crucial role in ecosystems, maintaining plant dynamics and shaping landscapes. For example, giant sloths, by consuming leaves, facilitated the spread of certain plant species, which in turn affected other animals. With the disappearance of these large mammals, ecosystems began to change, leading to an increase in the number of small species and changes in plant structure. As a result, by the end of the Pleistocene, many megafauna species were unable to adapt to the new conditions, and their extinction marked a significant moment in Earth's history. While some species, such as bison and deer, managed to survive and adapt, others, like mammoths, became victims of the combination of climatic changes and human activity. Modern research on frozen remains of mammoths in permafrost helps scientists understand how these changes occurred. For instance, recent discoveries on Wrangel Island, where well-preserved mammoth remains were found, indicate that the climate conditions of that time were significantly warmer than previously thought. This also opens new horizons for studying the interaction between humans and nature in the wild. The final extinction of megafauna, which occurred approximately 3,000 years ago, marked a turning point in ecosystems that began to form under the conditions of the modern climate. Meteorite craters are unique geological formations that testify to the constant interaction between Earth and space. Each time a celestial body, whether a meteorite or an asteroid, enters Earth's atmosphere, it leaves a trace that can persist in the geological record for millions of years. Studies have shown that there are more than 300 known meteorite craters on Earth, each resulting from collisions with celestial objects ranging in size from several meters to several kilometers in diameter. For instance, it is believed that one of the largest craters on Earth, the Chicxulub crater in Mexico, formed approximately 65 million years ago and is linked to the mass extinction of dinosaurs. These craters are not only important objects of study, but also serve as reminders of how vulnerable our planet is to the forces of space. Meteorites impacting Earth can cause catastrophic consequences, such as devastating explosions that can wipe out entire ecosystems and alter climate conditions. Scientists have found that even small meteorites, the size of a car, can cause significant damage. For example, in 1908, a meteorite that fell in the Tunguska region of Siberia caused an explosion equivalent to several atomic bombs and destroyed more than 2,000 square kilometers of forest. These events underscore that Earth is not an isolated world, but a part of a dynamic and sometimes dangerous cosmic system. The geological record of our planet is filled with such evidence. In the layers of sedimentary rocks, one can find tiny particles known as silicates and metals that form as a result of collisions. These samples help scientists reconstruct the history of collisions and assess their impact on climate and the biosphere. For example, the impact of a meteorite can release a large amount of dust and gas into the atmosphere, leading to a temporary cooling of the climate known as nuclear winter. Therefore, meteorite craters are not just geological formations, but archives of our planet's cosmic history, continuing to hold secrets and threats from the vast expanse of space. As of 2023, scientists continue to study these craters using modern technologies, such as satellite imagery and geophysical methods, to better understand their structure, age, and impact on ecosystems. The Arizona crater, also known as Meteor Crater, is one of the most impressive geological formations on our planet. It was created around 50,000 years ago, when a meteorite with a diameter of approximately 30 meters struck the Earth at a speed of about 27,000 kilometers per hour. This colossal impact created a crater with a diameter of about 1 kilometer and a depth of approximately 270 meters. Its dimensions are awe-inspiring. Standing at the edge, one feels small in comparison to this giant wound on the Earth's surface. The view from the cliff is breathtaking. Massive crater walls expose layers of rock, like pages of history, telling the story of geological processes that have taken place over millions of years. In its pristine condition, the crater serves as a living museum for geologists and tourists who come from all corners of the world to see this unique object. Special observation platforms allow visitors to appreciate the scale of the event that created this structure and understand that, in geological terms, it happened quite recently. The feeling of standing at the edge of the crater is enhanced by the realization of the power of nature, capable of such destructive but also creative phenomena. Inside the crater, one can see not only its size, but also the diversity of vegetation that is gradually recovering from the catastrophe that occurred millions of years ago. Research conducted by scientists shows that the crater is not only an object of study, but also an important indicator for understanding the processes that occurred on Earth and in its atmosphere. Meteor Crater has become a true symbol of Earth's collision with the cosmos, preserving traces of ancient catastrophes and reminding us that our planet is constantly subjected to external influences. In 2023, the crater continues to attract the attention of scientists who study its geological structure and try to understand how such events have influenced the climate and ecosystems over centuries. The Papagaï Crater, located in remote and hard-to-reach regions of Siberia, is one of the largest impact craters on Earth, with a diameter of approximately 110 kilometers. This crater formed as a result of a meteorite impact that occurred around 47 million years ago and remains a unique object for research. The Papagaï Crater is hidden under dense forests and taiga, making it difficult for researchers and tourists to access. However, this remoteness gives it a special atmosphere of mystery and grandeur, as if it holds the secrets of an ancient world. Around the crater, one can find numerous geological formations, including traces of volcanic activity and unique minerals formed due to the high temperatures and pressures resulting from the impact. One of the most intriguing aspects of the crater are the impact diamonds, which formed as a result of the rapid cooling of carbon-containing materials subjected to immense pressure during the impact. These diamonds, known as impact diamonds, can have unusual shapes and structures due to their formation process. Scientists like Dr. Georgy Petrov from the Institute of Geochemistry and Analytical Chemistry study these diamonds to understand how impact events can not only alter landscapes, but also affect the chemical composition of the Earth. Research shows that these diamonds have unique physical and chemical properties that differ from those of ordinary diamonds. For instance, they often contain inclusions of other minerals that provide information about the formation process of the crater and the conditions in which they were created. The Papagaï Crater is also considered an important object for studying climate and ecosystem changes that occurred on Earth after the impact. The crater serves not only as a monument to ancient catastrophes, but also as a laboratory for studying processes that took place in the Earth's interior millions of years ago. In 2023, despite the access difficulties, geologists and mineralogists continue to conduct expeditions to this unique region, aiming to uncover all its mysteries and understand how such impacts have influenced the course of Earth's evolution. As part of these studies, diamonds up to 1 millimeter in size have been found, which could provide insights not only into the history of Earth, but also into processes occurring in other planetary systems. The Tunguska event occurred on the morning of June 30th, 1908, over a remote taiga in Siberia, near the Podkamennaya Tunguska River. An explosion, caused by a celestial body, likely a meteorite or comet, released colossal energy equivalent to the explosion of several hundred atomic bombs. Investigations indicate that the explosion's power was estimated at 5 megatons of TNT or more. This resulted in the destruction of more than 2,000 square kilometers of forest, with trees uprooted, felled, and burned, forming a distinctive path of devastation visible from the air. However, what truly piques scientific interest and mystery is the absence of a crater or visible fragments, casting doubt on many theories about what happened that day. Some researchers have attempted to explain the lack of a crater by suggesting that the meteorite may have exploded in the atmosphere at an altitude of around 5 kilometers, disintegrating into numerous small fragments that burned up before reaching the surface. The site of the explosion has been the subject of intense study, but its remoteness and inaccessible nature have complicated the work. For researchers, this has been a true challenge, as there are no roads in the taiga, and access is only possible by helicopter or on foot. The first expeditions to this area consisted of local residents and scientists, such as Georgy Fedorovich, who conducted the first observations of the explosion's aftermath in 1909. During his research, He noted that trees within a radius of several dozen kilometers from the epicenter were knocked down but remained standing, as if no force had been exerted on them. This led to various theories about the nature of the event, ranging from meteorite hypotheses to more exotic suggestions about extraterrestrial civilizations. For decades after the event, scientists have attempted to find an explanation, proposing various versions, including explosions of gases hidden in the ground and even nuclear tests. But none of these theories could explain all the observed phenomena. In 1920, a research team led by Russian scientists such as Vitaly Sevastyanov and Boris Grigoriev returned to the explosion site, discovering that the soil retained abnormally high levels of radioactivity, adding another layer of mystery to this event. With each new investigation, new facts emerged, further highlighting the enigma of the Tunguska event and attracting the attention of both local and international scientists eager to unravel the mysteries of the cosmos. To this day, this event remains one of the most discussed topics in scientific circles, inspiring interest in all those who wish to solve this cosmic puzzle. There is even an initiative to create a special museum dedicated to the Tunguska event, which could gather all the research and artifacts related to this catastrophe. More than a century has passed since the explosion, and there is still no consensus on what exactly happened in the sky over Siberia. One thing is certain: the Tunguska event continues to be one of the most intriguing mysteries in the history of science. On February 15, 2013, at 2:14 p.m., an event occurred over Chelyabinsk that shook not only the local residents, but the entire world. A bright flash, brighter than the sun, illuminated the sky as a meteorite, weighing around 7,000 tons, entered the atmosphere at a speed of approximately 50,000 kilometers per hour. The shockwave from its explosion, equivalent to a throttle bomb with a power of 15 kilotons, hit the city, shattering windows in homes and tearing doors off their hinges. More than 300,000 windows were damaged, and around 1,500 people were injured, mainly from glass fragments. Many residents of Chelyabinsk became witnesses to this cosmic spectacle, which in an instant changed their everyday lives into something completely unimaginable. In the hours following the meteorite's fall, searches for its fragments began, attracting not only local, but also international scientists. Specialists from various research institutions, including the Institute of Earth Magnetism of the Russian Academy of Sciences, traveled to the fall site to study the aftermath of this cosmic invasion. In the center of Chelyabinsk, near Lake Chebarkul, where it was believed the main fragments of the meteorite fell, large-scale search operations began. Soon after the incident, several large chunks were found, the largest of which were between 30 and 60 centimeters in diameter. All found meteorite samples became objects of study, their composition helping scientists understand how celestial bodies formed in our solar system. The Chelyabinsk meteorite became one of the most thoroughly studied meteorites in history, leading to a new wave of scientific research related to cosmic threats. This case reminded humanity that celestial bodies are not just silent observers, but potential destroyers capable of invading anyone's life at any moment. Scientific circles began actively discussing the need for early warning systems for such threats. Nature once again demonstrated its power and unpredictability, leaving behind not only physical destruction, but also deep reflections on how humanity should prepare for a meeting with the cosmos. Since then, Chelyabinsk has become a symbol of the sudden collision of humanity with the cosmos, and the meteorite serves as a reminder of the constant threat posed by celestial bodies. The fragments of the meteorite found in Chebarkul are now in scientific collections and museums, where researchers continue to study them for new knowledge about the cosmos. Tsunamis are giant waves that can occur as a result of underwater earthquakes, landslides, or even impacts from celestial bodies. These waves form when energy released during an earthquake displaces vast volumes of water. For example, an earthquake with a magnitude greater than 6, occurring at a depth of less than 100 kilometers, can cause a sudden change in the underwater topography, raising or lowering the ocean floor. This creates energy that is transmitted through the water as waves. Interestingly, in the open ocean, tsunamis can be practically invisible, with their height reaching only a few tens of centimeters, making them dangerous because people often do not suspect the impending threat. However, when these waves approach shallow water, such as a coastline, their height begins to increase. This process is known as wave compression. Water moving in the ocean depths slows down, while the energy contained in the wave concentrates, causing a sudden increase in its height. For instance, the speed of a tsunami in open water can exceed 100 kilometers per hour, but as it approaches the shore, the wave can grow to 30 meters. This results in catastrophic consequences for coastal settlements, as the destructive power of a tsunami can be comparable to the force of an atomic bomb. The most dangerous tsunamis can cause not only flooding, but also significant destruction, sweeping buildings off the face of the earth. The mechanisms behind these processes make one ponder how vulnerable humans are in the face of nature. Modern tsunami warning systems, based on monitoring seismic activity and water levels, help reduce risks, but they are not always able to prevent tragedies. For example, in the case of a sudden meteorite impact causing a submarine earthquake, the reaction time may be minimal, making such events particularly dangerous. Tsunamis serve as a reminder of how quickly the world can change, and how the tranquility of the ocean can suddenly turn into the destruction of everything in the path of a giant wave. It is important to remember that tsunamis are not just waves. They are phenomena capable of changing landscapes and human fates in a matter of minutes. Ultimately, the power of nature knows no bounds and can manifest in the most unexpected forms, forcing humanity to always remain vigilant. The tsunami in the Indian Ocean, which occurred on December 26, 2004, was one of the most devastating natural disasters in history. Its cause was a powerful earthquake with a magnitude of 9.0 that struck at a depth of about 15 kilometers off the coast of Sumatra, Indonesia. The energy released by this earthquake was equivalent to the energy released by the explosion of more than 200 atomic bombs. The tsunami spread across the Indian Ocean at speeds up to 80 kilometers per hour, comparable to the speed of a jet aircraft. Waves reached heights of up to 30 meters in some places, sweeping away everything in their path, from villages to entire cities. When the waves hit the coasts, their height varied depending on the underwater terrain and the shape of the shoreline. For example, in some coastal areas of Sri Lanka and India, the waves grew in height, capturing and destroying everything in their path. The hardest hit were the Indonesian provinces of Aceh, where the waves destroyed almost everything on the coast, leaving only ruins and despair. Estimates suggest that more than 200,000 people died in 15 countries, including Thailand, Malaysia, Myanmar, and even the eastern coasts of Africa, such as Somalia. Rescue operations took place in the midst of a catastrophic humanitarian crisis, where millions were left homeless, without food, and without medical care. Recovery took years, and many countries faced long-term economic and social consequences. For example, in Indonesia, new tsunami warning systems were created, including meteorological stations and trained services capable of responding to such threats. A crucial aspect of this tragedy was that it highlighted the vulnerability of human communities in the face of nature's power and the need for preparedness for such disasters. The tsunami in the Indian Ocean served as a lesson for the world, prompting a rethinking of approaches to protecting against natural disasters. The tsunami of 2004 had a devastating impact on the coastal ecosystems, which became evident immediately after the disaster. Mangrove forests, which played a crucial role in protecting the coastline and served as habitats for numerous species, were particularly hard hit. As a result of the waves reaching heights of up to 30 meters, around 60% of the mangrove forests on the Indonesian coast were destroyed. These forests, which provided protection against erosion, lost their ability to recover, leading to increased losses in fisheries and deterioration of water quality. Coral reefs, vital for marine ecosystems, also suffered the consequences of the catastrophe. According to a study conducted in 2005, Around 40% of the reefs in the affected area were destroyed, threatening not only marine life, but also entire communities dependent on fisheries. The restoration of these reefs requires decades, and many scientists emphasize the need for active restoration programs, such as coral transplantation, which is a complex and labor-intensive task. Salinization of agricultural lands became another serious problem, as saltwater flooded fields where rice and other crops were previously grown. For example, in Sumatra, where around 7 million tons of rice were produced annually, the loss of arable land exceeded 30%. This led to significant economic losses and threatened food security for millions of people. The change in landscape caused by the tsunami also became a significant factor affecting ecosystems. New channels and silt deposits altered the usual migration paths of animals and fish, disrupting the balance in ecosystems. The restoration of nature was slow, and it was not until several years later that the first signs of life began to return to the affected areas. For example, in 2009, scientists noticed that young mangrove trees began to grow on previously destroyed areas, but their further development depended on the conditions of the surrounding environment and the level of pollution. Ecosystems that had lost their resilience required constant monitoring and care from local authorities and international organizations. The restoration of natural systems after the catastrophe became not only an ecological issue, but also a matter of social justice, as local communities had to adapt to new conditions and find ways to survive. The resilience of these ecosystems and their further development remain under threat, as climate change and human activity can exacerbate the situation. For example, by 2020, due to global warming, the sea level rose by 3 millimeters, adding another problem to the list for the affected territories. The restoration of ecosystems requires time, resources, and joint efforts to bring life back to the coast. Palico tsunamis are powerful natural disasters that have left clear traces in the geological record. Geologists study the deposits left by these ancient tsunamis to understand the scale and frequency of such events in the past. Research shows that such tsunamis have occurred over thousands of years, causing damage to coastal ecosystems and settlements. For instance, in 2005, a series of deposits were discovered in the Miyagi Prefecture of Japan, dating back to around 2,000 years before our era. These deposits contain sand and gravel brought in from the sea, indicating strong floods caused by tsunamis. Geologists use radiocarbon dating to determine the age of these deposits and analyze their structure and composition to reconstruct the dynamics of the events. In the case of paleo-tsunamis in the Pacific Ocean, researchers found that the maximum wave height could reach 30 meters, comparable to modern tsunamis caused by earthquakes. Comparing these data with historical records allows for a more comprehensive understanding of the frequency and strength of such events. For example, a study conducted in 2017 by scientists from Hokkaido University showed that at least 10 major tsunamis had occurred in the region over the past 5,000 years. Additionally, geologists use geomorphological methods to study the landscape altered by ancient tsunamis. In places like the coast of New Zealand, raised marine deposits have been found that show how ancient waves changed the landscape. This not only helps in studying the past, but also in predicting potential risks for future generations. For example, such research has led to the creation of maps of vulnerable territories, which assist local authorities in developing strategies to protect the population from potential threats. In 2018, after studying paleo-tsunamis in Indonesia, it was found that some coastal areas have a high risk of repeated flooding. Thus, the study of paleo-tsunamis not only opens doors to our past, but also provides crucial data for assessing risks and preparing for future disasters. Geologists continue to search for new samples and conduct analyses to better understand how often and with what force these catastrophic events occurred. In 2020, in the area of Sicily, layers of deposits were found that indicate a powerful tsunami that occurred around 500 years ago. These findings confirm that disasters like tsunamis can occur not only during earthquakes, but also as a result of underwater volcanic eruptions or landslides. Each new layer of deposits adds information about the past and helps in more accurate forecasting of future risks. Earthquakes are sudden and powerful underground shocks that occur due to the sudden displacement of blocks of the Earth's crust. These displacements occur at the boundaries of tectonic plates, where plates interact with each other, creating stress that eventually exceeds the strength of the rocks. When this happens, energy stored in the form of deformation is released, causing seismic waves. There are several types of these waves, including primary P waves, which are compressive and travel the fastest, and secondary S waves, which move slower and cause lateral oscillations. P waves can pass through both solid and liquid media, while S waves can only travel through solid materials, making them particularly useful for determining the internal structure of the Earth. Upon reaching the surface, these waves cause various types of vibrations, which can be classified as vertical or horizontal. Vertical vibrations often result in uplift and subsidence, while horizontal vibrations can cause buildings to shift and collapse. For example, during the 1994 Northridge earthquake in California, vibrations reaching 30 centimeters were recorded, leading to significant infrastructure damage and loss of human life. Earthquakes can occur at any time, and their unpredictability makes them particularly dangerous. They often happen without any prior warnings, exacerbating the situation for residents in high-risk areas. The expected strength of the shocks can range from weak, barely noticeable, to catastrophic, capable of destroying entire cities. For instance, the 1923 Great Kanto earthquake in Tokyo, which claimed the lives of over 100,000 people, was a disaster not only due to the force of the shocks, but also due to the subsequent fires that engulfed the city. It is also important to note that seismic waves can cause secondary phenomena, such as tsunamis, when underwater earthquakes occur on the ocean floor. These waves can reach enormous heights, as seen during the 2004 Indian Ocean earthquake, which resulted in a catastrophic tsunami that claimed the lives of more than 200,000 people in several countries. The effects of earthquakes are diverse and can vary depending on the depth, location, and type of soil on which structures are built. For example, dense rocks transmit seismic waves faster than loose ones, which can affect the extent of the damage. As a result, buildings on soft ground often experience more severe damage than those on solid foundations. Earthquakes remain one of the most complex and unpredictable natural phenomena that humanity has faced throughout its history. In the 20th century alone, Japan recorded more than 7,000 earthquakes, highlighting the activity in this region. The Great Lisbon earthquake occurred on November 5, 1755, and was one of the most devastating natural disasters in European history. This earthquake reached a magnitude of around 7.5 on the Richter scale, causing significant damage in the Portuguese capital of Lisbon, where more than 60,000 people perished due to the collapse of buildings. Massive stone and wooden structures, intended to last for centuries, could not withstand the powerful tremors. As a result of the earthquake, sudden and destructive fires broke out, engulfing the city and exacerbating the scale of the tragedy. Moreover, several hours after the main shock, a tsunami with a height of up to 30 meters struck the coast of Lisbon, sweeping away everything in its path, including buildings, people, and entire neighborhoods. This triad of disasters, earthquake, tsunami, and fires, caused mass panic and chaos, making this day one of the most tragic in the city's history. The destruction was so extensive that almost no building in Lisbon could withstand the force of nature. The entire city was left in ruins, and even famous churches like the Cathedral of St. Irene were practically destroyed. The Portuguese government, facing the magnitude of the destruction, quickly began the process of reconstruction, but Lisbon remained in a state of ruin for many years. This event not only shook Lisbon, but also sparked deep philosophical debates across Europe about the nature of evil and divine providence. Many thinkers, such as Voltaire and Rousseau, began to question how such a massive catastrophe could occur and how it related to their beliefs in a benevolent God. Voltaire, in particular, in his work Candide, ridiculed the philosophy of optimism, arguing that the phrase, "all is for the best in this best of all possible worlds," seemed hypocritical in the face of such disasters as the Lisbon earthquake. This tragic event also served as a catalyst for the development of seismology as a science. Scientists began to systematically study earthquakes, their causes and effects, leading to a deeper understanding of plate tectonics and the mechanics of the Earth's interior. One of the first researchers to study the earthquake was the Portuguese philosopher and naturalist Maria Monteiro, who began collecting data on earthquakes and their consequences. By establishing the first seismological station in Lisbon, he laid the foundations for modern seismology. This tragic experience became a lesson for all humanity, making us realize the fragility of human existence and the necessity of a scientific approach to understanding natural disasters. The earthquake affected not only Lisbon but the entire continent, changing people's views on nature and their place in the world. As a result, Lisbon became a symbol of both the destructive power of nature and humanity's desire to understand and control these forces. In the beginning of April 1906, San Francisco experienced the wrath of nature when one of the most devastating earthquakes in the history of the United States occurred. The force of the shock reached 8 on the Richter scale, and many residents did not even have time to realize what was happening. The rupture of the Earth's crust along the San Andreas Fault served as the catalyst for this catastrophic event, causing the ground to shake and crack like fragile glass. On the streets where life and vibrant activity once thrived, people in panic sought shelter, but many buildings collapsed, leaving behind only debris. In just a few minutes, the city, with a population of around 400,000, became a scene of chaos and destruction. However, the collapse of buildings was only the beginning of the calamities. Damaged gas pipes and stoves sparked massive fires that engulfed the city in a matter of hours. Estimates suggest that around 25,000 buildings were destroyed, which accounted for 80% of the city's construction. The flames rising against the gray sky looked like hell, and residents, trying to save themselves, could not leave their homes surrounded by fire. Firefighters, who tried to contain the inferno, faced unforeseen difficulties. They lacked water, and many hydrants were damaged during the earthquake. The chief of the fire department, Colonel Edward F. Hiley, declared that such conditions were unprecedented in his long career. Rescue workers labored day and night, but the fire continued to spread, consuming everything in its path. For 3 days after the earthquake, the fire engulfed neighborhoods where houses, stores, and cultural institutions once stood, leaving only ashes and ruins. The city, which was once a symbol of progress and prosperity, turned into a gloomy wasteland where panic and despair reigned. Thousands were left homeless, and humanitarian organizations such as the American Red Cross were at the center of efforts to assist the victims. Estimates suggest that more than 3,000 people died as a result of the catastrophe. This tragedy not only changed the face of San Francisco, but also left an indelible mark on the hearts of its residents. By the time the fire was finally extinguished, the city needed years of restoration. The restoration of San Francisco became a symbol of human spirit, resilience, and willpower. But the memories of those terrible days remained forever in the minds of those who survived the disaster. Many residents left the city, and those who stayed began to rebuild their lives among the ruins, realizing that nature can be both creative and destructive. As a result of the earthquake and the subsequent fires, San Francisco lost not only its buildings but also its soul, and the restoration became not only a construction process but also an emotional challenge for the entire community. Devastating earthquakes, such as those that occurred in San Francisco, have served as catalysts for the development of earthquake-resistant construction. Following the 1906 earthquake, which claimed the lives of more than 3,000 people, engineers and architects began actively seeking ways to create buildings that could withstand seismic tremors. The city's reconstruction required not only the repair of damaged buildings, but also innovative solutions aimed at preventing such catastrophes in the future. At this time, the study of seismic waves and their effects on structures became active. One of the first significant steps was the introduction of damping technologies. For instance, in the 1970s, Japan developed systems that included the use of special devices to absorb the energy of vibrations. These devices, known as dampers, are installed inside buildings and help reduce vibrations, significantly increasing the stability of structures. In 1988, after a powerful earthquake in Mexico, with a magnitude of 8.2, architect José Guillermo Echeverría managed to create skyscrapers with flexible structures that not only resist seismic vibrations, but also allow buildings to play during tremors, reducing the risk of collapse. These flexible structures, made of steel and concrete, were designed with the local climate and soil conditions in mind, demonstrating their effectiveness during subsequent earthquakes. The use of special materials, such as high-strength concretes and lightweight composite materials, also became an important part of earthquake-resistant construction. For example, in 2012, after the devastating earthquake in Christchurch, New Zealand, buildings were constructed using new composite materials that were several times lighter than traditional ones, significantly reducing the load on foundations. Modern architects and engineers use computer models to simulate the behavior of buildings during earthquakes, allowing them to predict how structures will react to various levels of seismic activity. In 2015, in California, a project for a new residential complex was developed, utilizing advanced analysis and design methods, which made it possible to create buildings that could withstand tremors with a magnitude of up to 8. This work requires constant learning and adaptation, as each new structure must take into account the unique geological and climatic conditions of the region. As a result, modern technologies and approaches to earthquake-resistant construction not only protect buildings, but also help save lives during earthquakes. Over the past decades, the implementation of advanced technologies has significantly reduced the number of destructions and casualties in earthquake-prone areas. For example, in Japan, where earthquake-resistant technologies have been integrated into mass construction, the number of casualties from earthquakes has decreased by more than 80% over the past 30 years. Early warning systems for earthquakes are complex and highly advanced networks capable of detecting seismic activity and transmitting signals in mere seconds. In Japan, a country where earthquakes are a part of daily life, one of the most effective early warning systems, known as J-Alert, has been developed. This system utilizes a widespread network of seismometers placed across the entire country. For instance, over 30 seismometers are installed in Tokyo, capable of detecting even the slightest ground movements. When a seismometer detects primary waves, P waves, which travel faster than destructive waves, S waves, the information is immediately transmitted to a data processing center where algorithms developed by scientists analyze the received data. These algorithms can distinguish genuine earthquake signals from noise, thus preventing false alarms. Upon confirmation of system activation, the signal is sent to emergency services and media outlets. It is crucial to note that every second counts. Even a 30-second warning can save lives by allowing people to take cover in safe places. Alerts are received through televisions, radio transmitters, and mobile phones, ensuring instant notification of the population. In Hokkaido, for example, approximately 7 million residents received warnings 12 seconds before a strong earthquake in 2017, enabling many to take shelter in safe zones. Early warning systems are continually being improved, and new technologies such as artificial intelligence are enhancing prediction accuracy and data processing speed. For instance, in 2021, California implemented the Shake Alert system, which uses over 300 seismometers to monitor seismic activity and also sends warnings to residents' mobile devices, giving them a few seconds' notice of impending danger. Scientific research indicates that well-organized early warnings can reduce the number of casualties by 30%, highlighting the importance of such systems in modern cities where millions live in high seismic risk areas. In Chile, following a powerful earthquake in 2010, the government developed a program based on Japan's experience and created a network of seismometers along the coast. The system was successfully tested in 2012, when residents received a warning 18 seconds before an earthquake of magnitude 8, preventing mass casualties. This race against time, where every second is crucial, demonstrates how modern technologies can significantly enhance safety and minimize the impact of natural disasters. The climate of Earth has undergone numerous changes throughout its geological history, and these changes are part of a natural cycle that has been ongoing for millions of years. During this time, the planet has experienced periods when levels of carbon dioxide in the atmosphere were significantly higher than today, leading to what are known as greenhouse states. In such times, temperatures could rise by 10 degrees Celsius or more compared to current levels. During these periods, tropical forests could extend to polar regions, and oceans were warmer and more diverse in life. For example, during the Cretaceous period, which lasted from 130 to 60 million years ago, sea levels were hundreds of meters higher than today, and Earth was almost free of glaciers. At the same time, the planet has also experienced ice ages, when vast ice sheets covered significant parts of the northern hemisphere. During periods such as the Pleistocene, which lasted approximately 2 million years and ended around 10,000 years ago, temperatures dropped to critically low levels, causing mass migrations of animals and humans in search of warmer places. These ice ages, when average temperatures were several degrees below current levels, led to the formation of extensive polar ice caps that covered Canada, Scandinavia, and even parts of Russia. Scientists like James Hutton note that such cycles of climate change occur under the influence of various factors: fluctuations in Earth's orbit, solar activity, and tectonic processes that change the location of continents and, consequently, ocean currents. Over the past 500 million years, Earth has experienced at least 5 major mass extinctions, each associated with rapid climate changes. For example, 300 million years ago, at the end of the Carbon period, oxygen levels in the atmosphere reached 30%, promoting the growth of plants and animals. However, when the climate became drier and colder, many species could not adapt and went extinct. There is also evidence that such changes occur on geological timescales, and the climate can change its state within a few thousand years. This indicates that Earth is not a static system, but a dynamic, constantly changing environment in which the climate responds to various internal and external factors. The variability of Earth's climate is an undeniable fact, illustrated by numerous geological and paleontological data, including the layered structure of deposits and fossil remains, which show how life and climate adapted to changing conditions. Scientific research shows that even small fluctuations in carbon dioxide levels can lead to significant changes in climate, highlighting the fragility and interconnectedness of the entire climate system of the planet. Today, scientists are recording that current rates of climate change exceed natural levels, causing concern among researchers who note that humanity may face consequences similar to those observed in the past, when ecosystems could not adapt to new conditions. It is important to understand that climate change is not just about temperature, but also about changes in precipitation, sea levels, and even the distribution of species. Periods of rapid warming in the past often coincided with mass extinctions and the reorganization of ecosystems, underscoring the importance of studying these processes to better understand our current situation. In particular, changes in the isotopic composition of carbon in sedimentary rocks allow us to reconstruct past climatic conditions and compare them with current trends. The Paleocene-Eocene thermal maximum occurred around 56 million years ago and was one of the most significant climatic events in Earth's history. During this period, the surface temperature of the oceans rose by 5 to 8 degrees Celsius. This rapid warming was caused by substantial emissions of carbon dioxide and methane, which, according to scientists, were likely triggered by volcanic activity, particularly in the area of modern-day northeast Greenland. These climate changes led to catastrophic consequences for both marine and terrestrial ecosystems. In the marine environment, there was a significant decrease in oxygen levels, resulting in mass extinctions of some marine organisms, particularly benthic and planktonic populations. Many fish and mollusk species were unable to adapt to the new conditions, leading to changes in food chains. On land, the increase in temperature facilitated the expansion of tropical forests into regions that were previously more temperate. For example, in the northern latitudes where tundras and taiga are now located, lush tropical forests thrived, inhabited by diverse plant and animal species. The emergence of new ecosystems also led to changes in the ranges of animals. For instance, many mammal species, such as primitive elephants and the ancestors of modern horses, began to migrate northward, where they could adapt to the new conditions. Conversely, species more sensitive to climate change faced the brink of extinction, significantly altering biological diversity. While some groups of organisms, such as crocodiles, managed to adapt to the higher temperatures, others, like some marine turtle species, encountered serious problems due to the changes in ecosystems. Numerous studies conducted by scientists have shown that during this time, there was rapid speciation and adaptation of species such as palms, which became more widespread in the new climatic conditions. Changes in the structure of ecosystems were also observed, including the expansion of tropical plant ranges and the disappearance of many species unable to withstand the climate changes. These processes illustrate how rapid warming can not only alter the climate, but also transform all life on the planet, including the impact on ecosystems and the species that inhabit them. Based on the analysis of carbon isotopes in the sedimentary rocks of this period, scientists have been able to reconstruct the climatic conditions and understand their impact on biota. In particular, the analysis showed that the level of carbon dioxide in the atmosphere reached values of around 1,000 parts per million, which is 2 to 3 times higher than current levels. These data emphasize that the causes and consequences of past climate changes have significant importance for understanding contemporary climate challenges. During the Paleocene-Eocene thermal maximum, which occurred approximately 56 million years ago, the primary cause of global warming was the massive release of methane from methane hydrates located on the ocean floor. Methane hydrates are crystalline formations that contain methane trapped within a water structure. These formations stabilize at low temperatures and high pressures, typical of deep ocean zones. However, as ocean temperatures rose due to initial warming, these methane hydrates began to decompose, releasing methane into the atmosphere. Scientists estimate that during this period, up to 30 trillion tons of methane could have been released into the atmosphere, significantly increasing the concentration of greenhouse gases. Methane, being a much more potent greenhouse gas than carbon dioxide, causes a rapid increase in temperature. Each molecule of methane is 25 times more effective at trapping heat in the atmosphere over 100 years compared to carbon dioxide. This created a positive feedback loop. Increased temperature led to additional methane release, which in turn caused further warming. As a result, the planet's climate system temporarily destabilized, leading to ecosystem changes and the extinction of various species. Isotope analysis of carbon shows that during this period, the level of carbon in the atmosphere rose to around 1,200 parts per million, which is several times higher than current levels. This explains why significant climate changes, including warmer temperatures at the poles and sea level rise, were observed during this time. Scientists believe that this process was similar to a chain reaction, where each release of greenhouse gases affected the next, creating conditions for catastrophic climate changes. Climate models indicate that such events could occur in the modern world if we continue to increase the levels of carbon dioxide and other greenhouse gases in the atmosphere. The Paleocene-Eocene thermal maximum serves as a warning about how quickly the climate can change under the influence of greenhouse gases. It is important to note that these changes occurred in the context of natural climate fluctuations. but the role of humans in contemporary warming is already significant. According to the International Energy Agency, the level of carbon dioxide emissions into the atmosphere increases by several percent each year, which could potentially lead to consequences similar to those in the past. Paleoclimatic studies based on the analysis of sediments and fossil records show that such changes in ecosystems can occur within a few decades. Snowball Earth is a hypothetical period in the history of our planet, when glaciers covered almost the entire surface, including equatorial regions. Such a global ice age is believed to have occurred several times in Earth's history, with the most well-known being the global glaciations. One of the most critical periods occurred approximately 700 million years ago at the end of the Neoproterozoic era, when the planet's temperature dropped to critical levels and glaciers covered even the equatorial zones, creating harsh conditions for life. At this time, oceans froze almost to the equator, and life on Earth as we know it was under threat of extinction. Photosynthesis, the primary process that sustains life on the planet, almost ceased due to the polluted atmosphere and lack of sunlight, which could not penetrate the thick ice cover. Studies show that in such conditions, life could only exist in isolated refuges, such as hot springs, deep-sea hydrothermal vents, and subglacial lakes. For example, on the ocean floor, there are thermal springs where the temperature reaches 120 degrees Celsius, and it is there that some microorganisms could survive by using chemical synthesis. These organisms would form the basis of ecosystems that could develop in complete isolation from the rest of the world. Scientists studying such conditions suggest that these hot springs could have been centers of biomass concentration, making them vital for understanding the evolution of life on Earth. While the planet's surface was covered with ice caps, unique ecosystems could have existed in the depths of the oceans, where life adapted to extreme conditions. For instance, in such conditions, organisms capable of chemosynthesis, using hydrogen sulfide and other chemical compounds, could have survived in complete darkness. As modern research shows, during such periods, Earth could have been in a snowball state, where glaciers extended from the poles to the equator, creating a continuous ice shell. This state could have lasted for millions of years, and only through significant changes in climate and atmosphere did life begin to spread across the planet's surface again. One example of such changes was the increase in the level of carbon dioxide in the atmosphere, which could have led to global warming and the melting of glaciers. Therefore, research into ancient climatic conditions and their impact on the development of life remains relevant to scientists, helping to better understand how our planet coped with such catastrophic changes. These data also assist in assessing contemporary climate changes and their possible consequences for life on Earth. The transition from the snowball Earth state is a complex and dramatic process in which volcanic gases, particularly carbon dioxide and methane, play a crucial role. During the time when Earth was covered by a thick layer of ice, volcanic activity, such as the eruptions of supervolcanoes like Toba in Indonesia, contributed to the accumulation of significant amounts of these gases in the atmosphere. One of the largest eruptions occurred approximately 68,000 years ago, when the release of ash and gases altered the composition of the atmosphere. The increase in carbon dioxide concentration enhanced the greenhouse effect, as this gas absorbs infrared radiation and traps heat, creating conditions for temperature rise. As a result of this process, when temperatures began to rise, ice caps started to slowly melt, which in turn contributed to further increases in greenhouse gases, as the melting ice released methane that had been trapped in glacial deposits. This methane, which has a heat-trapping effect 25 times greater than carbon dioxide, amplified the greenhouse effect, leading to rapid global warming. With each passing year, as glaciers retreated, oceans warmed, increasing water evaporation, which also added water vapor, a powerful greenhouse gas, to the atmosphere. For example, around 30,000 years ago, the atmospheric carbon dioxide level was approximately 280 parts per million, whereas by the end of the last ice age, this figure had risen to 400 parts per million. Consequently, the ice fields that once covered much of the planet began to rapidly disappear, giving rise to new ecosystems and altering the landscape. Scientific research indicates that by the end of the last ice age, around 10,000 years ago, the global temperature had risen by an average of 3 to 4 degrees Celsius, which served as a catalyst for the emergence of modern climatic conditions. At this time, ice in the Arctic and Antarctic had significantly diminished, and new maritime routes had opened, facilitating human and animal migration and the development of the biosphere. A key moment in this process was when the carbon dioxide level exceeded a certain threshold, creating a self-reinforcing cycle in which higher temperatures led to further ice melt, which in turn increased sea levels and altered ocean currents. As a result of these changes, many animal and plant species were forced to adapt or go extinct, leading to significant shifts in biogeographical distribution. In the last few decades, we have witnessed mass extinctions of animals and plants in the Anthropocene, occurring at an unprecedented rate. According to researchers, current rates of species extinction are tens to hundreds of times higher than the natural background rate of one extinction per million species per year. For comparison, the World Wildlife Fund reports that we are currently losing up to 100 species per day, a result of human activity. The main factors contributing to this phenomenon include the destruction of natural habitats, climate change, environmental pollution, and excessive exploitation of natural resources. For instance, deforestation for agriculture, which covers millions of hectares of tropical forests annually, leads to the destruction of unique ecosystems such as the Amazon rainforest, home to numerous species found nowhere else. According to UNEP, around 75% of all Earth's ecosystems have been significantly altered by human activity, posing a critical threat to existing species. Climate change, caused by greenhouse gas emissions, leads to changes in temperature regimes, sea level rise, and shifts in precipitation patterns, negatively impacting both aquatic and terrestrial ecosystems. As a result, many species cannot adapt to these new conditions, leading to their extinction. Research shows that in the Anthropocene, we are not only witnessing quantitative but also qualitative changes in ecosystems, where some species are displacing others, leading to a loss of biological diversity. It is important to note that the primary culprit behind this global ecological crisis is one species, Homo sapiens, who, with the unique ability to alter nature, has become the cause of global transformations. The fact that more than half of all species on Earth are threatened with extinction requires us to rethink our relationship with nature and ecosystems. Notably, the extinction of one species can trigger a chain reaction affecting many others, underscoring the complexity and interconnectedness of ecosystems. Statistics indicate that more than 40% of amphibians and 30% of mammals are on the brink of extinction, threatening the stability of entire ecosystems and their services to humans. Research shows that ecosystems rich in species diversity are more resilient to changes, and their loss can lead to a decrease in productivity and a change in ecosystem functionality. It is crucial to understand that mass extinctions in the Anthropocene are not just statistics, but a real threat to our planet and future generations. Each species that disappears from the face of the Earth is not only a loss of biological diversity, but also a loss of opportunities for medicine, agriculture, and sustainable development. For example, many modern medicines are based on compounds found in plants and animals that may disappear before we have a chance to study them. The situation requires not only scientific understanding, but also active measures at the political and societal levels to prevent further destruction of ecosystems that support life on the planet. The adoption of sustainable practices in agriculture, the protection of natural reserves, and the restoration of degraded ecosystems are important steps in combating this global problem. According to a UN report, by 2030, it is necessary to halve the rate of species extinction to preserve biological diversity for future generations. Effective measures to combat climate change, such as transitioning to renewable energy sources and reducing carbon emissions, also play a key role in slowing this process. It is not surprising that without specific actions to protect ecosystems and biological species, we may be on the brink of an ecological catastrophe. Currently, more than 1 billion people depend on forests for their livelihoods, highlighting the importance of preserving these ecosystems. The disappearance of the megafauna of the Holocene in Australia is one of the most mysterious and tragic events in the continent's history. Around 40,000 years ago, when the first members of the Homo sapiens species arrived on the Australian continent, they encountered a unique, isolated ecosystem inhabited by giant marsupials like the megatherium and large birds, such as the dromornis. These animals, which had evolved in the absence of large predators, were not prepared for the arrival of humans, who quickly took on the role of predators. Australia had been developing in isolation for millions of years, and its fauna had no experience with such threats. The disappearance of large herbivores, such as the diprotodon, which weighed up to 3 tons, and other megafauna, led to significant changes in ecosystems. The loss of these animals altered the balance of nutrition and resulted in an increase in the number of plants that were previously controlled by large herbivores. This affected the vegetation of the continent, causing it to spread and change typical ecosystems. For example, in the absence of large herbivores like the megatherium, which could maintain the balance, there was a growth of shrubs, which in turn changed the fire regime. Fires became more frequent and intense, as the accumulation of tall grasses and shrubs became highly flammable. With the arrival of humans, active hunting of megafauna began, along with changes in the landscape for agriculture and pastures. These actions accelerated the disappearance of megafauna, leading to further changes in ecosystems. Around 12,000 years ago, the megafauna of Australia was almost completely wiped out. Research shows that such changes were the cause of the loss of biodiversity and climate change in the region. As a result of the disappearance of these animals and the changes in the ecosystem, Australian forests became less diverse and more prone to fires, which also affected the climate conditions. Currently, it is believed that by the end of the Pleistocene, that is, the beginning of the Holocene, most large species had disappeared, leaving only a small number of representatives, such as kangaroos and koalas. These events underscore the importance of understanding the interaction between humans and nature, as well as the impact of humans on ecosystems. The dodo, also known as the dronte, was a flightless bird that inhabited exclusively the island of Mauritius. It was discovered by Europeans in the late 16th century. When the first Portuguese explorers arrived on the island in the 16th century, dodos already inhabited its shores, lacking natural predators, which led to their fearlessness and lack of caution around humans. The dodo reached a height of 1 meter and weighed around 10 kilograms. Its large body, covered in gray feathers and characterized by a plump belly, made it an easy target. Despite having atrophied wings, the dodo adapted well to its isolated environment. The 18th century proved to be disastrous for the dodo, as in 1638, Dutch settlers arrived on the island and began actively hunting these birds. Soon, sailors and colonists joined in, using dodos as a food source, unaware of the unique species they were decimating. The first accounts of the dodo were recorded by the Dutch naturalist Willem de Vlaming, who described it as a bird that does not fear humans. By the beginning of the 17th century, the dodo population was rapidly declining. The situation worsened with the introduction of pigs, cats, and rats to the island, which began eating dodo eggs and their chicks, further reducing their population. As a result of hunting and habitat destruction, the dodo disappeared from the face of the earth within less than 100 years of the island's discovery. The last reliable sightings of the dodo date back to 1662. By the end of the 17th century, its existence was reduced to stories and legends. The study of dodo remains found in the late 19th century confirmed that this species had gone extinct, serving as a symbol of the tragic misunderstanding of the value of unique ecosystems and their inhabitants. Scientific research has shown that the dodo lacked natural enemies and did not develop defensive mechanisms against hunting, making its extinction a stark example of the catastrophic consequences of human activity. Modern methods of preserving endangered species include various approaches aimed at preventing extinction and restoring biodiversity. One of the most common methods is captive breeding. For example, at the California Condor Recovery Center, established in 1983, the California condor has been successfully bred in captivity. In the early 1990s, their population declined to just 27 individuals, but thanks to the efforts of scientists and volunteers, the number of condors has increased to over 400 by 2020. Key to the program is not only captive breeding, but also reintroduction into the natural habitat, which requires careful preparation and monitoring. Genetic material cryopreservation also plays a crucial role in the conservation of biological species. Programs like the Frozen Ark project, which began in 2001, are focused on collecting and storing DNA samples, cells, and sperm from endangered species. This allows for the preservation of genetic diversity and, if necessary, the restoration of populations in the future. Currently, the Frozen Ark holds over 50,000 samples from various animals, creating a reservoir for future breeding and reintroduction programs. Restoring ecosystems is also a vital part of efforts to preserve biodiversity. For instance, in New Zealand, active projects are underway to restore habitats where animal species have disappeared. The Project Island Song initiative, launched in the early 2000s, involves planting new plants and establishing protective zones on islands previously inhabited by rare birds to restore their populations. Scientists are working to reintroduce species such as kiwi and tuis back into their natural habitats. Environmental organizations like the World Wildlife Fund, WWF, implement global initiatives to protect endangered species, including population monitoring and anti-poaching measures. In 2020, WWF launched a program to protect elephants in Africa, which resulted in a 30% reduction in poaching in areas where conservation efforts were actively conducted. The importance of these efforts cannot be overstated, as each species plays a unique role in the ecosystem. For example, bees pollinate more than 30% of agricultural crops, and their disappearance not only threatens biodiversity, but also food security. Research shows that preserving biodiversity has a direct impact on the health of ecosystems, resilience to climate change, and economic stability. In 2019, the United Nations announced a goal to restore 1 billion hectares of degraded land by 2030, highlighting the importance of international cooperation in environmental conservation and the preservation of endangered species. Anthropogenic climate change represents one of the most significant challenges facing humanity. This process is driven by human activity, which leads to an increase in the concentration of greenhouse gases in the atmosphere. In particular, carbon dioxide, produced as a result of burning fossil fuels such as coal, oil, and natural gas, plays a key role in this process. In the 18th century, the level of carbon dioxide in the atmosphere was around 280 parts per million, while by the 21st century, this figure had risen to more than 400 parts per million. This increase enhances the greenhouse effect, where solar energy is trapped in the atmosphere, leading to global temperature rises. The feedback loop between temperature increases and other climate processes also intensifies. The melting of Arctic ice reduces Earth's reflectivity, leading to further warming. For example, in 2009, NASA scientists recorded record rates of melting in the Greenland ice sheet, which was one of the first clear signs of accelerating climate change. Rising ocean temperatures cause them to expand and rise, threatening coastal cities and ecosystems. Additionally, climate change affects precipitation cycles, leading to both droughts and floods, which in turn impact agriculture and water resources. In 2018, the World Meteorological Organization reported record levels of precipitation in some regions of the world, a result of changing climate conditions. The interactions between various climate factors are becoming increasingly complex and unpredictable. For instance, rising temperatures facilitate the release of methane from permafrost, which is a more potent greenhouse gas than carbon dioxide. It is important to note that many ecosystems are unable to adapt to the rapidly changing conditions, leading to the extinction of species and the destruction of biomes. In 2020, scientists recorded the disappearance of more than 1,000 animal species, indicating a growing imbalance in ecosystems. All these changes create a sense of growing chaos and uncertainty in the planet's climate system, where human activity not only exacerbates existing processes, but also triggers new, unpredictable mechanisms. The intensification of conflicts over resources such as water and land is already evident in various regions of the world, making the problem of climate change not only an environmental, but also a social one. By 2020, the number of people suffering from water scarcity had exceeded 2 billion, underscoring the severity of the situation. Therefore, anthropogenic climate changes have become an integral part of our existence, requiring urgent and decisive action. The melting of Arctic ice is occurring at an alarming rate, as confirmed by data collected by satellites and scientific expeditions. In 2020, the area of sea ice in the Arctic Ocean reached its lowest levels in recorded history, covering only 3 million square kilometers, which is 30% less than the average for the 20th century. This reduction in area is accompanied by a decrease in the thickness of the ice cover. According to a study conducted in 2019, the average ice thickness has decreased by 1 meter over the past 30 years. The white reflective surface of the ice, which previously hindered the absorption of sunlight, is giving way to dark water, creating a positive feedback loop that exacerbates warming in the Arctic. Each square meter of open water absorbs significantly more heat than ice, leading to an increase in the temperature of the surrounding environment. As a result, over the past 50 years, the average temperature in the Arctic has risen by 3 degrees Celsius, which is twice as fast as the global average. This change in climate is fundamentally altering the conditions for local ecosystems. The populations of marine mammals such as seals and polar bears are decreasing due to the reduction in ice cover, which is necessary for their hunting and reproduction. Indigenous peoples, such as the Inuit, are facing serious problems as their traditional ways of life, based on hunting and fishing, are threatened. Changes in ecosystems also affect the migration of fish, negatively impacting fishing, which is the primary source of food for these communities. In 2006, a study conducted by the Arctic Institute found that around 70% of Inuit face difficulties accessing traditional food resources. Changes in climate conditions are also leading to changes in Arctic ecosystems. Forests are gradually moving north, replacing tundra, which disrupts the natural balance. These changes not only affect nature, but also cultural traditions passed down through generations. The opening of new sea routes, such as the Northern Sea Route, creates additional economic opportunities, but also increases the risk of pollution and conflicts over resources. In 2020, the level of carbon dioxide in the atmosphere reached record levels, underscoring the need for urgent measures to combat climate change. The melting of Arctic ice is becoming not only an ecological, but also a social catastrophe. The melting of the Greenland and Antarctic ice sheets is one of the most alarming ecological problems of our time. Ice shields that have existed for tens of thousands of years are losing their stability at an alarming rate. For example, in Greenland, the melting rate has increased nearly threefold since 2006. In 2020, scientists from the University of Copenhagen discovered that more than 31 billion tons of ice disappeared from the surface of Greenland in a single year, equivalent to a 1 millimeter rise in sea level. The situation in Antarctica is no less critical. A study conducted in 2019 showed that the melting rate of Antarctic ice shelves has increased by 40% over the past 50 years. This is due to warm ocean currents penetrating under the ice shelves, causing their destruction. For instance, the Thwaites Glacier in West Antarctica, known for its rapid calving of icebergs, is losing mass each year. In 2020, researchers recorded the calving of an iceberg larger than 1,000 square kilometers from this glacier, one of the largest events in recent years. Such calving events occur due to intense underwater melting, where warm ocean waters erode the ice walls. As a result, massive icebergs formed in this process become enormous floating masses that pose not only a threat to navigation, but also a significant factor in climate change. For the first time in the history of observations, in 2018, an iceberg that broke off from the Antarctic Peninsula reached an area of more than 300 square kilometers and became the largest recorded iceberg since 2002. These changes do not occur in a vacuum. Each year, the melting of glaciers contributes to the rise in global sea levels, which, according to projections, could reach 1 meter by the end of the century. This threatens the flooding of coastal cities such as Mumbai and New York, where millions of people could be at risk. Additionally, changes in the ice cover affect global ocean currents and climate systems, creating a chain reaction that can impact the entire world. Studies show that glacier melting leads to changes in ocean salinity, which, in turn, can alter the migration routes of marine organisms and affect fisheries. The global climate is becoming more unstable, meaning that phenomena such as hurricanes and floods may become more frequent and intense. At this time, when we observe these slow but inexorable changes, it is important to remember that the consequences affect not only polar regions, but the entire human race. Studies show that the level of carbon dioxide in the atmosphere continues to rise, exacerbating the problem. In 2020, the level reached record values, more than 400 parts per million. Rising sea levels are becoming one of the most serious threats to coastal territories worldwide. 80% of the Earth's population lives within 100 kilometers of the coast, and this number is growing. Melting of glaciers, both in Greenland and Antarctica, as well as the thermal expansion of water due to global warming, are causing the sea level to rise by an average of 3 millimeters per year. According to the Intergovernmental Panel on Climate Change, if temperatures continue to rise, sea levels could rise by 1 meter by the end of the 21st century, flooding millions of hectares of land. Low-lying coastal areas, such as the Mekong Delta and Bangladesh, are already experiencing problems with flooding and erosion, and this is just the beginning. In regions such as the Maldives, where the average height above sea level is only 1 meter, the threat of flooding becomes critical. For instance, a study in 2019 showed that at the current rate of sea level rise, the Maldives could become virtually uninhabitable by 2050. Coastal cities like New York and New Orleans are also at risk, already facing challenges with flooding and hurricanes that are becoming increasingly destructive. The need for infrastructure adaptation is evident. Cities must invest in flood protection systems such as dikes and pumping stations. For example, the Netherlands has developed a comprehensive protection system including protective walls and movable barriers, which allows it to successfully manage flood threats. However, adaptation is not limited to engineering solutions. Population migration from flooded areas is becoming a reality. By 2030, up to 70 million people may become climate refugees, leaving their homes in search of safety. In this context, island nations such as Tuvalu and Kiribati, which could completely disappear from the world map, are particularly vulnerable. These countries are already considering the possibility of relocating their populations to other countries, such as New Zealand, which has offered visas to citizens of Tuvalu. In the face of such uncertainty, governments must develop sustainable policies aimed at protecting the population and their means of livelihood, as well as the development of new, safe places to live. The shift in rainfall patterns due to global warming is becoming increasingly evident, and its consequences are catastrophic for many regions of the world. Since the beginning of the 20th century, the average global temperature has risen by 1 degree Celsius, leading not only to changes in temperature regimes, but also to sharp fluctuations in the distribution of rainfall. According to the Intergovernmental Panel on Climate Change, in some regions, such as Sub-Saharan Africa and Southeast Asia, there has been a significant increase in the frequency and intensity of droughts. For instance, in Southern Africa, droughts now occur every 3 to 4 years, resulting in reduced agricultural yields and famine. Meanwhile, in other parts of the world, such as North America and Europe, there has been a sharp increase in the amount of rainfall, leading to flooding. Summer floods in Europe, which used to occur once every 10 years, are now becoming regular, as seen in the case of the 2020 flooding in Germany, where the water level in rivers rose by 4 meters, inundating entire cities and claiming the lives of more than 100 people. These extreme weather events not only cause damage to infrastructure, but also threaten traditional agricultural practices. Farmers are facing new challenges, as methods that worked for decades are now proving ineffective. For example, in India, where farmers relied on seasonal rains for irrigation, the change in rainfall patterns has led to widespread crop failures. In some areas, rain is now falling in short but intense downpours, while other regions are experiencing drought. This creates catastrophic conditions for agriculture, which requires predictability and stability. In such conditions, adaptation becomes a real challenge, as traditional agricultural planning and urban construction methods no longer provide the necessary resilience. In light of these changes, governments need to develop new strategies to cope with the increasing unpredictability of climate conditions. Experts emphasize the need to integrate modern technologies in water resource management and agriculture to minimize the impact of these climate changes. For instance, the use of drip irrigation systems can help reduce water consumption during droughts, and modern drainage systems can prevent flooding in cities. However, these solutions require significant investments and time to implement, and not every country has the resources to do so. Projections indicate that by the year 2030, due to climate change, the number of people experiencing food shortages worldwide could increase to 100 million. Adapting to new climate conditions requires not only technological changes, but also a fundamental restructuring of socio-economic systems, which poses a serious challenge for many states. The increasing unpredictability of weather we are experiencing underscores the need for urgent action and a strategic approach to planning the future. Geoengineering is a concept that involves deliberate human intervention in Earth's climate system to combat global warming. This idea emerged at the end of the 20th century as scientists began to recognize that anthropogenic factors, such as carbon dioxide and methane emissions, significantly impact the climate, causing it to change. According to the Intergovernmental Panel on Climate Change, since the start of the industrial era, the level of carbon dioxide in the atmosphere has increased by more than half, leading to a rise in the planet's average annual temperature. In this situation, geoengineering can serve as a potential tool to mitigate the consequences of climate change, but it also presents significant ethical and scientific risks. The main challenge lies in the fact that interfering with the climate system can lead to unpredictable consequences. For example, attempts to manage solar radiation could alter rainfall patterns in certain regions, resulting in droughts in some areas and floods in others. Studies show that even small changes in the climate system can have catastrophic effects on ecosystems and agriculture. In this context, scientists and policymakers face a difficult choice: risk inaction and allow the situation to worsen, or take action and encounter possible unexpected effects. It is important to note that any actions in the field of geoengineering require global consensus and strict control, as they can affect not only individual countries, but the entire planet. In the early 2000s, discussions began about the need for international norms and rules to regulate research in this area, but there are still no clear international agreements that define these boundaries. There are also questions of fairness. Who will be responsible for the consequences of intervention? Considering that the least developed countries typically suffer the most from the effects of climate change, the question arises of how to ensure that geoengineering projects do not exacerbate existing inequalities. Some researchers, such as Professor Ken Caldera, emphasize that before taking any action, it is necessary to carefully weigh the pros and cons and conduct extensive research into the possible consequences. At the same time, ignoring the problem of climate change is becoming increasingly dangerous, and by the end of the 21st century, billions of people may face serious climate challenges. In such conditions, geoengineering may become one of the possible solutions, but its application must be thoughtful and considered. The ethical dilemmas associated with this topic remain relevant, and it will take a long time to find a balanced approach that allows the use of technologies without unnecessary risk. Studies show that if research in the field of geoengineering is not conducted, the consequences of climate change could become catastrophic. Spraying aerosols in the stratosphere is one of the most discussed geoengineering technologies aimed at reducing global temperature. The essence of this technology lies in artificially creating an effect similar to volcanic eruptions, where small particles are released into the atmosphere that can reflect solar radiation. A striking example of such a process is the eruption of the Pinatubo volcano in the Philippines in 1991, which resulted in a decrease in the average global temperature by about 0.5 degrees Celsius over the next 2 years. This was due to the release of a large amount of sulfuric gas and ash into the stratosphere, which formed an aerosol cloud that reflected sunlight and thus cooled the Earth. In the context of geoengineering, it is proposed to use a similar approach by spraying sulfate aerosols, such as ammonium sulfate, into the stratosphere at an altitude of around 20 kilometers using special canisters or modified aircraft. One such project is the Stratospheric Controlled Perturbation Experiment, scheduled for 2023, in which scientists plan to test aerosol spraying and assess its impact on the climate. However, despite the potential benefits, there are serious concerns about the side effects associated with the use of this technology. Aerosol spraying could lead to changes in precipitation patterns, which in turn could affect agriculture and the availability of fresh water in various regions of the world. Studies show that an increase in aerosol concentrations in the atmosphere can lead to changes in global weather patterns, resulting in more intense and frequent hurricanes, as well as droughts in some areas. Furthermore, another important aspect is the impact on the ozone layer, which protects the Earth from ultraviolet radiation. Scientists are concerned that the introduction of sulfate aerosols could negatively affect its condition, increasing the level of ultraviolet radiation reaching the surface. Since the ozone layer is already under pressure due to human activities, additional risk factors could exacerbate existing problems. Therefore, spraying aerosols in the stratosphere could temporarily reduce global temperature, but its application requires a thorough assessment of the possible consequences for the climate, ecosystems, and human health. Before implementing such technologies in practice, a deep understanding of all the risks and opportunities associated with their use is required. Currently, there is no consensus on the advisability of using aerosols for geoengineering, and it is necessary to consider the opinions of both supporters and opponents of this technology to arrive at a balanced decision. Carbon capture and storage, CCS technologies, which involve capturing and storing carbon, represent a complex and multifaceted process aimed at reducing the concentration of carbon dioxide in the atmosphere. The fundamental principle is to directly capture CO2 from the air, purify it, and store it long-term, such as in geological formations. These technologies require the creation of infrastructure comparable in scale to the oil industry, but with the opposite goal. Instead of extracting carbon from the Earth, we need to return it. Direct capture of CO2 from the atmosphere is achieved through various methods, one of which is the use of adsorbents, materials that can bind CO2 molecules. In the 20th century, this process began to develop in laboratory conditions, and since the early 2000s, companies like Climeworks in Switzerland have started implementing it on an industrial scale. In 2020, Climeworks opened its first direct air capture plant in Iceland, capable of capturing up to 400 tons of CO2 per year. Scientific research indicates that to have a significant impact on the climate, we need to capture billions of tons of CO2 annually, which requires scaling the technologies to a level where they become economically viable. It is important to note that the captured CO2 can not only be stored, but also converted into useful products such as synthetic fuels or building materials, opening new economic horizons. However, despite the potential, there are significant challenges related to logistics and economic feasibility. Creating a network of pipelines for transporting CO2 to storage sites requires enormous investments and meticulously designed infrastructure. For example, in the United States in the 21st century, plans were developed to create a system of pipelines that would connect CO2 sources with underground storage facilities in various states. These projects could require tens of billions of dollars and several years to implement, raising questions about the speed and scale of CCS technology deployment. Regarding storage, CO2 can be injected into depleted oil or gas fields, which have proven their ability to retain carbon for millions of years. Experts estimate that there are enough geological formations worldwide to store trillions of tons of CO2. However, to achieve this level, it is not only necessary to develop the technology, but also to convince governments and private companies to invest in it. In the 21st century, various initiatives were presented, such as the Net Zero project from the International Energy Agency, which emphasizes the need for active use of carbon capture and storage technologies to achieve carbon neutrality. In this context, it is worth noting that some large companies operating in the fossil fuel sector have begun investing in CCS as part of their strategy to reduce emissions. For example, the oil giant BP announced plans to invest in carbon capture projects in the North Sea, which could serve as an example for other companies. Another important aspect is the need to develop efficient and affordable CO2 capture methods, as high costs could become the main obstacle to widespread adoption of the technologies. In 2022, a new method was presented in California that reduces the cost of CO2 capture by 30% compared to traditional methods. It is important to note that without significant improvements in efficiency and cost reduction, CCS technologies may remain an interesting but small-scale solution. Therefore, despite all technological advances, we face significant challenges that require a comprehensive approach and substantial resources to create a system capable of effectively managing carbon emissions. Natural solutions for carbon sequestration, such as reforestation, wetland restoration, and marine ecosystem restoration, are becoming increasingly important in the fight against climate change. Forests, for instance, are among the most effective natural carbon sinks. According to the World Health Organization, 1 hectare of mature forest can absorb up to 12 tons of carbon dioxide per year. Reforestation is not only a means of carbon sequestration, but also a way to preserve biodiversity. In tropical forests like the Amazon, more than 25% of all known animal and plant species reside, highlighting the importance of these ecosystems for protecting biological diversity. Wetland restoration also has its advantages. Wetland ecosystems can store carbon in the form of organic material that accumulates in their waterlogged areas. Research shows that restored wetlands can absorb carbon at a rate of up to 11 tons per hectare per year. Additionally, they serve as important barriers against floods, as they absorb excess rainfall and regulate water levels in surrounding ecosystems. Restoration of marine ecosystems, such as mangrove forests and seagrasses, is also crucial. Mangrove forests, for example, can absorb carbon 2 to 3 times faster than terrestrial tropical forests and protect coastlines from erosion and hurricanes. According to UNEP, mangrove ecosystems store up to 10 billion tons of carbon, making them some of the most valuable natural resources for carbon sequestration. Such ecosystems not only help in the fight against global warming, but also provide vital services such as improving water quality, creating habitats for fish and other marine organisms. It is important to understand that the health of ecosystems is directly linked to their ability to sequester carbon. For example, the degradation of forests and wetlands leads to the release of carbon into the atmosphere, exacerbating the problem of climate change. According to the UN, global deforestation results in carbon emissions equivalent to more than 12 billion tons of carbon dioxide annually. To effectively utilize these natural solutions, it is necessary to develop comprehensive strategies that consider local conditions, ecosystem characteristics, and economic factors. In some regions, such as Indonesia, programs for mangrove forest restoration have already demonstrated their effectiveness, increasing carbon stocks and improving the living conditions of local communities. Ecosystem restoration requires time and resources, but the results can be impressive. Scientific research shows that the restoration of natural ecosystems can lead to an increase in biomass and, consequently, to greater carbon sequestration. It is important to note that such approaches can be part of a broader strategy to reduce carbon emissions, including carbon capture and storage technologies. For example, in Sweden, methods that combine reforestation with modern carbon capture technologies are actively used, allowing for the most effective use of natural resources in the fight against climate change. Research shows that the combination of natural and technological solutions can lead to significant reductions in carbon emissions in the future. In the vicinity of Earth, there are constantly present objects that pose a potential threat to our planet. These objects range in size from small meteoroids to large asteroids, with their total number estimated at hundreds of thousands. Every week, Earth encounters meteors the size of gravel, which, after passing through the atmosphere, burn up without reaching the surface. This phenomenon, known as a meteor shower, occurs regularly and is often unnoticed by humans. However, while most of these objects are too small to cause significant damage, there are larger meteoroids capable of causing catastrophic consequences. For example, in 1989, a small asteroid known as ATLAS passed within 22,000 kilometers of Earth, much closer than geostationary satellites. Thus, our planet is constantly moving through space, where millions of objects orbit the solar system. Many of these objects can cross Earth's orbit, posing potential threats. Asteroids typically form in the asteroid belt between Mars and Jupiter, where their number is counted in millions. These objects remain in unstable orbits and can be ejected onto trajectories that cross Earth's orbit, especially under the influence of planetary gravitational forces. Research shows that large asteroids larger than 100 meters can cause damage on a national or even continental scale. An example of such an event is the Tunguska meteorite that fell in Siberia in 1908, causing an explosion that burned more than 2,000 square kilometers of forest. This incident demonstrates that even relatively small objects can have enormous consequences. According to scientists, the probability of Earth colliding with an asteroid larger than 1 kilometer in diameter is 1 in 500,000 per year, which, although low, is a cause for serious concern. Scientific research and monitoring of objects in the vicinity of Earth have become a priority for many space agencies, including NASA and the European Space Agency. These organizations use various methods for detecting and tracking asteroids, including radar systems and telescopes operating in different light ranges. For example, the NEOWISE program, launched in 2009, discovered thousands of new objects and provided important data on their sizes, orbits, and compositions. Scientists use this data to assess potential threats and develop strategies to protect Earth from possible collisions. One such strategy involves changing the trajectory of an asteroid using gravitational influence or direct impact with a spacecraft. Test missions like DART are aimed at studying these technologies and their effectiveness in real conditions. Thus, while we often perceive our planet as a safe haven, in reality, it is moving through a cosmic ocean filled with potentially dangerous objects. The constant presence of these asteroids and meteoroids underscores the need for continuous study and monitoring of our near-Earth environment. Scientific research shows that even small changes in the orbits of these objects can have significant consequences for life on Earth. In this context, it is important to remember that space is full of surprises, and our planet is moving through a space filled with potential threats. Astronomers and scientists continue to work to better understand the dynamics and orbits of these cosmic objects, which will allow us to more effectively protect our civilization from possible catastrophes. Currently, there are more than 7,000 known objects that cross Earth's orbit, and their number continues to grow each year. Astronomers worldwide are actively involved in programs for detecting and cataloging near-Earth objects, utilizing modern telescopes and algorithms. One of the key tools in this field is the Pan-STARRS telescope located in Hawaii. Since its launch in 2008, it has discovered more than 30,000 asteroids that cross Earth's orbit. Pan-STARRS uses a wide-field camera that allows it to scan large areas of the sky in one night, significantly speeding up the detection process. Additionally, telescopes like Catalina Sky Survey and Linear also contribute by covering various parts of the night sky. To process the collected data, astronomers use specialized algorithms that help identify moving objects against the background of stationary stars. For example, the Moving Object Detection algorithm highlights moving objects by analyzing changes in images taken over short periods. Once an object is detected, its orbit is calculated using mathematical models based on celestial mechanics laws, such as Newton's law of universal gravitation. This process involves multiple observations of the object to accurately determine its position and velocity. Modern methods allow for precise data on the trajectory, which is critically important for assessing the potential danger of each discovered asteroid or comet. For instance, NASA has developed a system called Sentry, which automatically analyzes data and evaluates the probability of collision for detected objects with Earth. It is important to note that this system checks for potential collisions over the next 100 years and provides information on the probability, which can reach, for example, 0.1%. International cooperation plays a significant role in these efforts. Astronomers from different countries exchange data to improve the quality of observations and ensure more comprehensive sky coverage. For example, the European Southern Observatory is actively involved in a project to monitor near-Earth objects, which allows for the pooling of resources and technologies for more effective detection. As a result of these collaborative efforts, astronomers were able to discover asteroid Apophis, which in 2030 will pass within 38,000 kilometers of Earth, less than the distance to geostationary satellites. Therefore, programs for detecting and cataloging near-Earth objects are becoming increasingly important for protecting our planet from potential threats. In 2021, more than 7,000 near-Earth objects were registered, and the number of discoveries continues to grow. In the last few decades, the concept of protecting Earth from asteroid threats has become an active topic of discussion among scientists, engineers, and government organizations. One of the most discussed methods is the use of kinetic impactors, which are spacecraft capable of colliding with a threatening asteroid at high speed and altering its trajectory. For example, in 2020, NASA launched the DART Double Asteroid Redirection Test mission, which involved a collision with the Dimorphos asteroid in 2022. Scientists plan to assess how effectively the asteroid's orbit can be changed, which would be a significant step towards the practical application of this technology. Gravitational tractors, another concept, involve using spacecraft that, while in close proximity to an asteroid, can gradually shift its orbit using their gravitational pull. This process takes time, but unlike kinetic impactors, it involves a more gentle impact on the target object. Research in this area is ongoing, and in 2020, a group of scientists from MIT presented a concept that could allow small satellites to use gravitational forces to alter the trajectory of a large asteroid. Nuclear explosions are another method that is actively discussed in scientific circles. The idea is to detonate a nuclear device on the surface of an asteroid to create a powerful impulse that can shift it off its dangerous trajectory. Although this method raises many ethical and practical questions, including potential consequences for the asteroid and the Earth's environment, it continues to be researched. In 2020, scientists from the University of California, Los Angeles, published results of their calculations showing that a properly calculated nuclear explosion could effectively shift the orbit of an asteroid up to 400 meters in diameter. These methods highlight that humanity is transitioning from passive observation of cosmic threats to an actively aggressive stance, integrating scientific achievements in aerospace technologies and astrophysics to ensure the safety of the planet. As technologies develop, the possibility of creating effective protection systems becomes increasingly real, and in the next few decades, humanity may acquire tools to prevent catastrophic collisions with asteroids, allowing us to become not just victims of the cosmos, but active participants. Currently, work is being done on creating international programs aimed at uniting the efforts of various countries in the fight against asteroid threats, which also reflects the growing understanding of the need for cooperation in this area. In 2020, the first International Symposium on Planetary Defense was held, where experts from more than 40 countries gathered to discuss strategies and methods for protecting Earth from potential dangers at the level of global cooperation. The idea of protecting the planet from cosmic threats has become an integral part of modern scientific discourse, and today we can see real steps towards the realization of these ambitious plans. Within NASA's mission to study near-Earth objects, conducted in 2020, approximately 76 new asteroids were registered, underscoring the need for the development of effective protection methods. International cooperation in the field of planetary defense is becoming increasingly relevant as the threat posed by space objects knows no boundaries. In 2020, countries participating in the European Space Agency's program signed an agreement on joint monitoring of near-Earth asteroids. This agreement allows for the integration of data from various telescopes and observatories, including the Arecibo Observatory in Puerto Rico and the Keck Observatory in Hawaii. Joint efforts in asteroid observation have already yielded results. In 2020, around 76 new objects were registered, underscoring the need for coordination in international efforts to protect the planet. Specialists from different countries, including the United States, Japan, and Russia, began conducting regular video conferences to exchange data on potentially dangerous asteroids. In 2021, during such a conference, the possibility of a collision between asteroid Bennu and Earth in the 22nd century was discussed. Assessments showed that the risk was 1 in 8,000, which, although not causing panic, still requires attention and further research. A significant step in international cooperation was the creation of NASA's DART program, which is designed to test asteroid deflection technology, and joint tests are scheduled for 2022. Specialists from Europe and Japan are participating in this project, demonstrating unity among countries in addressing a common problem. Discussions on joint missions to explore asteroids usually take place at meetings within the UN framework, where countries can share experience and technological achievements. For example, in 2020, at a meeting of the UN Committee on the Peaceful Uses of Outer Space, a project for a joint mission to study asteroid Apophis, which will pass close to Earth in 2023, was presented. This project includes not only observations, but also the development of strategies for protection against potential threats in the future. Initiatives like Astronomy for Development also involve countries of the Third World in international cooperation, allowing them to participate in global efforts to explore space. The creation of an international database of space objects was another important milestone. In 2016, the Space Situational Awareness Platform was launched, which integrates data from various countries and institutions. This allows not only to track threats, but also to unite efforts for more accurate forecasting of possible collisions with Earth. In the face of global instability, the threat from space becomes a factor that unites humanity, requiring the overcoming of political differences for the common security of all Earth's inhabitants. The safety of the planet becomes a priority, and such initiatives as international missions and data exchange emphasize the need for global interaction and joint search for solutions. In 2020, the number of discrepancies in data on space objects between countries decreased by 30% due to joint work. In the future, a supercontinent will emerge as a result of the slow but inexorable movement of tectonic plates over tens of millions of years. Currently, according to geological data, continents are moving at a speed of about 2 centimeters per year, which seems insignificant on a human scale, but in geological time, it leads to significant changes. For example, millions of years ago, at the end of the Paleozoic era, continents united to form the supercontinent Pangaea, which existed for about 300 million years and began to break apart approximately 180 million years ago. This process of disintegration served as a catalyst for the formation of modern continents and oceans, such as the Atlantic Ocean, which continues to expand each year. In the future, in 50 or 100 million years, some continents may begin to converge again, forming a new supercontinent. Scientific research indicates that such a situation could arise due to a combination of subduction, where one plate descends beneath another, and continental collision, where continents collide. For instance, in the Indian Ocean, the Indian plate continues to collide with the Eurasian plate, leading to the formation of the Himalayas, whose height increases by several millimeters each year. Remarkably, throughout these processes, life on Earth will continue, adapting to the constantly changing conditions. Research shows that even after the disappearance of humanity, which may occur within the next several million years, geological processes will continue to shape the planet's landscape. At that time, oceans will change their positions, and continents such as Australia will gradually move north, colliding with Asian lands. Moreover, as a result of these tectonic changes, new mountain ranges, similar to the Alps or Andes, and new oceans may emerge, separating the newly formed continents. These changes will occur over millions of years, maintaining a continuous cycle of birth and destruction characteristic of our planet. The geological record of Earth shows that such transformations occur with regular periodicities, and the remnants of previous supercontinents, such as Gondwana, can be seen in mountain ranges and the distribution of fossilized remains. Therefore, the formation of a new supercontinent will be just one stage in an endless cycle of tectonic activity that will continue without pause, regardless of whether humans exist or not. Tectonic plates, like enormous mosaic tiles, will continue to move, collide, and separate, creating new geography over millions of years. The model of the future supercontinent, known as Pangaea Ultima, predicts that approximately 250 million years from now, all continents will once again unite into a single landmass. This concept was proposed by geologists at the beginning of the 21st century and is based on current data on the movement of tectonic plates. According to estimates, Pangaea Ultima will be more compact than its predecessor, with a shape resembling a giant oval or drop, where the central part will be occupied by massive mountain ranges formed as a result of continental collisions. This supercontinent will be primarily located in the southern hemisphere, with the equator passing through its eastern part, leading to significant climatic changes. In the center of Pangaea Ultima, extremely continental conditions are expected, where average temperatures can reach 30 degrees Celsius, and in some areas, even higher values are possible. This is due to the remoteness from oceans, creating unique conditions where rainfall will be minimal and humidity will be extremely low. On the coasts, on the other hand, the climate will be more moderate, with mild temperatures and high levels of precipitation provided by the proximity to oceans. The hypothetical model suggests the existence of a large internal sea, which may arise due to tectonic activity and will be located between different continental masses. This sea will provide more diverse ecosystems than in the center of the supercontinent. Some scientists, such as Jonathan Kendall from the University of Leeds, predict that such changes will lead to the creation of completely new ecosystems and adaptations of species that can survive in conditions of sharp climatic fluctuations. According to the model, continents such as North America, South America, Africa, and Asia will move towards each other at a speed of about 12 centimeters per year, which is generally consistent with the rates observed in previous geological epochs. They will collide, forming new mountain ranges, such as potential high ranges similar to the Alps or Himalayas. These mountain formations will have a significant impact on the local climate, creating rain shadows and changing wind directions, which in turn will affect the distribution of flora and fauna. However, Pangaea Ultima will not be a static formation. The processes leading to the formation of the supercontinent will continue even after its formation, causing continents to spread apart and collide again, as they have done for millions of years. This constant movement of plates and change in the position of continents will create a dynamic and changing planetary environment. As a result, after several tens of millions of years, Pangaea Ultima may again break up into several continents, which in turn will evolve and adapt to new conditions. Thus, Pangaea Ultima will become not only a geographical, but also an ecological experiment, which will be observed by an entire epoch, where life may take forms that we can hardly imagine now. Research based on modern modeling and comparative geology continues to refine this hypothesis, confirming its foundations and identifying possible scenarios. Scientific forecasts show that changes occurring in the Earth's interior will affect the entire biosphere, shaping landscapes and ecosystems that will exist in conditions of thermodynamic stress. In the future, the climate on the supercontinent will be a complex mosaic of extreme conditions that will be significantly different from today's climatic zones. Interior regions, far from the oceans, will experience sharp temperature fluctuations, possibly ranging from -30 to +50 degrees Celsius, depending on the time of year. Such conditions will create vast arid areas where annual rainfall does not exceed 100 millimeters. Research indicates that these arid regions may occupy up to 70% of the supercontinent's land area. At the same time, coastal areas will be subject to monsoon winds that will bring heavy rains during certain seasons. The location of the supercontinent, with its wide equatorial zones, will facilitate the development of these monsoons, as hot air will rise and interact with cooler coastal currents, creating powerful cyclones. These conditions will make most of the land unsuitable for complex forms of life. Biodiversity in this world will be concentrated in narrow strips along the coasts, where the humid monsoon climate will allow the development of tropical forests with high plant density and species diversity. For example, research shows that such ecosystems may concentrate more than 70% of all known species, creating unique conditions for survival and adaptation. In contrast, interior regions will be deprived of moisture, and the survival of species will be a real challenge. Some organisms may adapt to extreme conditions by developing the ability to conserve water and protect against high temperatures. For instance, plants with deep roots and hard leaves may become dominant in these conditions, while animals such as rodents or reptiles may survive by hiding in underground burrows during the hottest hours of the day. There are data indicating that similar conditions existed in the past, during the Paleozoic era on Earth, when large supercontinents such as Pangaea existed, and their interior regions also experienced significant climatic changes. While the coasts were inhabited by diverse marine creatures, the interior areas remained largely barren and uninhabitable for life. The future supercontinent is likely to resemble these ancient landscapes, creating a world where life is concentrated in narrow strips, and the natural environment becomes a true arena for survival. Scientific models predict that, despite the extreme conditions, life will not disappear completely. It will simply adapt to new challenges, forming unique ecosystems that will differ from anything we have seen before. Scientific research shows that in such conditions, symbiotic life may develop, where organisms will depend on each other in their struggle for survival. In a world where humanity has long since vanished, life not only persists, but also rapidly evolves, filling ecological niches left empty by the departure of humans. Over millions of years, starting from the 21st century, organisms have adapted to changing conditions, including climate changes, fluctuations in sea level, and the emergence of new ecosystems. Research indicates that after a mass extinction caused by human activity, such as climate change and habitat destruction, nature has demonstrated an extraordinary ability to recover. For instance, by the 32nd century, former megacities like New York and Tokyo were replaced by dense forests, where trees like the metasequoia and eucalyptus developed resistance to high temperatures and drought, characteristic of the new climate conditions. These trees became the foundation of new ecosystems, where unique animal species adapted to life in dense forests and urban jungles. For example, scientists discovered that some mammalian species, such as large rodents, evolved to sizes comparable to dogs to better protect themselves from predators. These creatures developed a unique survival strategy. They became omnivorous and learned to use various food sources, including fruits, tree bark, and even insects. Meanwhile, in the conditions of increased radiation left from nuclear disasters, some microorganisms, such as bacteria Deinococcus radiodurans, developed the ability to repair DNA and became key participants in new food chains. These microorganisms became the basis for new forms of life, including microscopic animals that can survive in extreme conditions and form symbiotic relationships with larger organisms, allowing them to utilize resources unavailable to others. Adaptations also concern marine ecosystems. With the disappearance of humans, large planktonic organisms began to develop in the oceans, occupying niches previously filled by fish and becoming the main producers of oxygen on the planet. Square meters of coral reefs, once suffering from bleaching, now serve as homes for diverse forms of life, such as colorful sea stars and exotic mollusks, which evolved to live in conditions of increased water acidity. In such conditions, new groups of organisms emerged, developing unique mechanisms of protection from predators, such as bright colors or toxic secretions. By the 35th century, according to paleontologists, it became possible to observe the adaptation of terrestrial animals, such as lizards, which began to develop the ability to move more efficiently on vertical surfaces to avoid predators and find food in trees. This led to the formation of new lizard species that became inhabitants of the heights, developing special adaptations, such as a changed composition of claws and body shape. In this new ecosystem, life continues to develop, taking forms that we can only speculate about today, including the creation of new symbiotic relationships between different groups of organisms. All these changes emphasize the remarkable ability of life to adapt and survive in conditions that once seemed insurmountable. In a world where humanity has disappeared, life on Earth continues its evolution, taking on new, unexpected forms. Scientific research shows that through millions of years, the planet may become a habitat for completely new organisms that will live in harmony with nature, as it was millions of years ago. Changes on Earth occur under the influence of numerous factors that have been acting over billions of years. From within, the planet continues to cool, leading to a decrease in volcanic activity and changes in tectonic processes. For example, over the last 100 million years, continents have slowly moved, contributing to the formation of new mountain systems and changes in climate. As continents move, oceans deepen, resulting in the formation of new marine ecosystems. These changes occur so slowly that they appear almost imperceptible to human perception, but in the context of geological time, they represent a massive transformation. The climate on the surface of Earth also undergoes constant changes. Research shows that over the past 3 million years, there have been both global warming and ice ages that have altered the planet's appearance. For instance, during the last ice age maximum, which occurred around 20,000 years ago, vast areas of North America and Europe were covered in ice up to 3 kilometers thick. This ice not only changed the landscape but also significantly impacted ecosystems, forcing animal and plant species to adapt or go extinct. From the outside, Earth is affected by solar activity, which also influences the climate. The level of solar radiation changes with a cycle of about 22 years, and these changes affect temperature, atmospheric phenomena, and even ocean currents. Examples of such phenomena, like El Niño, demonstrate how changes in ocean surface temperature can lead to global climate anomalies, including heavy rains and droughts. In addition, Earth is subject to the influence of cosmic factors such as asteroids and comets. Impacts from large celestial bodies can cause mass extinctions. For example, it is believed that a collision with an asteroid about 10 kilometers in diameter, which occurred around 65 million years ago, led to the extinction of the dinosaurs. This catastrophic event altered ecosystems and paved the way for the emergence of mammals, which eventually gave rise to humans. Over time, biological changes also occur on the planet. Evolution of species, adaptation to new conditions, migrations, and extinctions are all part of natural selection. For example, over the last 100,000 years, Homo sapiens have survived and evolved, overcoming various ecological and climatic challenges. In the process of colonizing new territories, humans have influenced nature, altering landscapes, flora, and fauna. Furthermore, human activity over the past few thousand years has led to changes in the atmosphere. Emissions of carbon dioxide and other greenhouse gases due to the Industrial Revolution and large-scale agriculture have resulted in global warming. Scientific research shows that the level of carbon dioxide in the atmosphere reached record levels, exceeding 380 parts per million in the 20th century. This causes climate changes that can have long-term consequences for all ecosystems on Earth. In the face of all this, it is worth noting that the history of human civilization is but a brief moment in the infinite time of Earth's existence. If we consider the temporal scales, human history occupies only a few tens of thousands of years, while Earth has existed for over 4.5 billion years. In this context, it becomes clear that the planet will continue to change, regardless of whether humanity exists or not. Each new geological period will create new conditions for life, and the traces of our civilization will eventually become mere specks on the pages of Earth's history. The molecules of water that currently form the oceans may one day be part of entirely different ecosystems, perhaps even on other planets, as humanity explores the cosmos. The sun is gradually becoming brighter, and this process will not stop. Scientists predict that over the next several 100 million years, the luminosity of our star will increase by 8%. This increase in brightness will cause the temperature on Earth to rise. Specifically, in about 100 million years, the average temperature on the planet's surface could rise by several degrees, which will already have a noticeable impact on the climate. As the temperature rises, oceans will begin to evaporate more actively, and sea levels may rise due to the increase in water volume in the atmosphere. Furthermore, during the evaporation of oceans, greenhouse gases such as water vapor are released, which further intensifies the greenhouse effect. Scientists predict that in about 300 million years, with the continuous increase in solar radiation, the temperature on Earth could exceed 100 degrees Celsius, making the planet completely uninhabitable as we know it. The biosphere will begin to retreat to the poles, where the temperature will be more favorable for survival. At this time, the ecosystems we know will be destroyed, and the surviving organisms will be able to exist only in narrow strips of cooler climate. The existence of complex life forms will become impossible, as most species will not be able to adapt to such extreme conditions. Oceans, once teeming with life, may turn into lifeless deserts, and the organisms left on the planet will have to compete for resources in harsh conditions. Additionally, the increase in solar radiation may cause changes in the atmosphere, including the destruction of the ozone layer, which will lead to even higher levels of ultraviolet radiation, harmful to living organisms. The future of Earth in this scenario becomes bleak, but despite this, the planet will continue to exist, changing in accordance with the new conditions. Over millions of years, in place of the current oceans, new geological formations may form, and in place of the destroyed biosystems, other, simpler organisms may arise, adapted to the new conditions. Scientists also note that ultimately, when the solar luminosity reaches its peak, Earth may become similar to Venus, where the temperature reaches more than 240 degrees Celsius, and the atmosphere consists mainly of carbon dioxide. This phenomenon is called the singularity of Venus, and it serves as a warning about how the future of Earth might unfold. The Sun, as a main sequence star, will continue its path until it enters the red giant phase, leading to a complete transformation of the solar system. At this critical moment, when the Sun begins to expand, it may engulf Mercury and Venus, and the impact on Earth will be catastrophic. Scientific models show that in about 700 million years, when the Sun is at its peak brightness, our planet may end up in a zone where life becomes impossible due to extreme temperatures and conditions. When the Earth cools and active plate tectonics cease, the planet will become geologically dead. Approximately 1 billion years from now, the internal heat necessary for maintaining convective flows in the mantle will be significantly reduced. This process will occur slowly but inevitably. The convection cells that once moved continents will quiet down. Continents, no longer subject to movement, will remain in their places, and their relief will gradually smooth out under the influence of erosion. Wind and water will relentlessly erode mountains that once towered above the surface, and after tens of millions of years, only undulating plains will remain in place of the once majestic peaks. Volcanic activity, necessary for renewing the Earth's surface and forming new lands, will become a mere memory, as magma will no longer rise from the depths of the mantle. Elements essential for life, such as carbon and nitrogen, will no longer be recycled into new forms. The cycling of these substances will be disrupted, leading to the degradation of ecosystems. Oceans that once teemed with life will become lifeless, as the lack of volcanic activity will result in the disappearance of new minerals necessary for supporting marine organisms. The disappearance of tectonic activity will also lead to the stagnation of the atmosphere. Without tectonic processes, there will be no release of carbon dioxide, which is necessary for maintaining the climate. As a result, the temperature on the Earth's surface will become unstable, exacerbating conditions for existing forms of life. Around 2 billion years later, when the planet has cooled completely, the mantle will become virtually motionless, and all geological processes that once shaped the landscape will cease. As a result, Earth will resemble a dead planet, like Mars, where there is no tectonic activity, and the relief has remained unchanged for millions of years. There will be no new mountain ranges, and rivers and lakes subject to erosion will gradually disappear, leaving only traces of their existence. Plate tectonics, as a crucial mechanism for maintaining the planet's dynamism, will fade into the past, leading to the creation of a static, unchanging world. In 5 to 7 billion years, our sun will transform into a red giant, forever altering the appearance of the solar system. At the beginning of this process, when the hydrogen reserves in the star's core are depleted, helium fusion will commence, leading to a significant increase in temperature and pressure in the core. As a result, the outer layers of the sun will begin to expand, continuing until it reaches the orbit of Mars. By this time, Mercury and Venus will be engulfed by the scorching sun, while Earth will face the threat of annihilation. Oceans will evaporate, the atmosphere will become thin, and life as we know it will be under threat of complete extinction. Initially, the surface temperature of Earth will rise to 1,000 degrees Celsius, and then, as the sun continues to expand, the planet will become a scorched, barren world. Under the influence of cosmic radiation and strong solar wind, the atmosphere will gradually dissipate, leaving behind only the charred ruins of the former paradise. On the horizon, a giant red disk of the sun will appear, occupying a large portion of the sky and illuminating the scorched surface of Earth, as if the star itself is concluding its long journey with a fiery spectacle. At this moment, Earth will not just be a lifeless planet, but a reminder of the life that once thrived here. The entire process will take millions of years, and in the end, only a planet with a cooled surface, where oceans and atmosphere once existed, will remain. The solar system as we know it will be destroyed, and only dust and debris will remind us of the life that once existed. The red giant will emit light sufficient to illuminate the desolate surface, but not enough to sustain life. The sun, having reached its peak, will become a symbol of finality and transformation, when stars, like all living things, reach their logical conclusion. Scientific research indicates that this process may begin in 5 billion years, when our star enters a new phase of its existence. The geological heritage of Earth is a unique chronicle, inscribed in its rock formations, that reflects the dynamic history of the planet over billions of years. Each layer of sedimentary, igneous, and metamorphic rocks is a page in the book that tells the story of catastrophes, ecological changes, and the evolution of life. For instance, sedimentary rocks can contain traces of ancient seas that once covered vast areas, while igneous rocks bear witness to volcanic activity that shaped landscapes. These geological records, formed through processes such as erosion, deposition, and metamorphism, preserve information about climatic changes, tectonic shifts, and even mass extinctions like the Permian or Cretaceous periods. Interestingly, some rocks can be dated using radiometric methods, such as uranium-lead dating, which allows scientists to determine the age of rocks and understand the temporal framework of geological events. Scientific research shows that studying these layers can reveal how life adapted to changing environmental conditions, as seen in fossil remains. For example, some layers may contain fossils of dinosaurs that lived around 150 million years ago, or traces of early mammals that appeared around 200 million years ago. Each discovery adds a new dimension to our understanding of Earth's evolution and its inhabitants. Notably, the geological heritage is not limited to fossils. It also includes minerals and ores that have been used by humanity throughout its history, from the Stone Age to the present day. Volcanic rocks like basalt and andesite testify to powerful eruptions that formed continents and oceans, while metamorphic rocks like gneiss and schist tell of the effects of high temperatures and pressures that altered the original minerals. Scientists studying the geological heritage use methods such as stratigraphy, paleomagnetism, and isotope analysis to reconstruct Earth's past and understand how it influences the current climate and ecosystems. For example, data on paleoclimate obtained from the analysis of glacial deposits show how the climate has changed over the last millions of years, which is crucial for predicting future changes. This rich archive not only helps us understand how life on the planet adapted to challenges, but also suggests how we can better manage resources and respond to changes in the environment. The geological heritage of Earth is not just a collection of rocks. It is a living history, reflecting the struggle and survival that has continued for billions of years. With each new discovery, we gain the opportunity to delve deeper into understanding how conditions for life were formed, what the planet was like before us, and how we can use this knowledge to preserve our habitat. In this context, it is important to note that geology provides us with tools for understanding not only the past, but also the future, allowing us to look into the depths of time and see how Earth has changed and continues to change. Specialists like geologists and paleontologists encounter new discoveries every day that add to this great picture. For example, in 2020, an international team of scientists discovered ancient traces that show how early mammals moved across the surface, leaving their footprints in sedimentary deposits. This process of continuous discovery and study becomes the key to understanding not only the history of Earth, but also our place in it. All this information is stored in layers that, like books, open up only to those who are willing to read them. The study of ancient catastrophes requires the use of diverse methods that enable scientists to reconstruct events that occurred millions and billions of years ago. One of the most effective tools for this purpose is isotope analysis, which helps determine the age of samples and the conditions under which they formed. For instance, using carbon-14 dating, based on the radioactive decay of carbon-14, researchers can accurately determine the age of organic materials, such as wood or bone, dating back up to 150,000 years. For older samples, uranium-thorium dating is employed, which allows for the determination of the age of calcite deposits formed in caves and can cover periods up to 300,000 years. Paleontological data also play a crucial role in understanding ancient catastrophes. By studying fossilized remains such as bones, teeth, and footprints, scientists can reconstruct past ecosystems and understand which species went extinct as a result of catastrophic events like asteroid impacts or volcanic eruptions. For example, in 2006, paleontologists discovered dinosaur fossils in China that contained traces of injuries, likely caused by catastrophic climate change, providing insight into how the extinction of dinosaurs might have been linked to global environmental changes. Geophysical research, such as seismic sounding and gravity measurements, allows scientists to study the structure of the Earth and identify traces of ancient catastrophes, such as earthquakes or volcanic eruptions. For instance, in 2018, scientists used three-dimensional seismic surveying methods to study the structure of underground layers in the area of an ancient volcano in Iceland, helping to identify potential risk zones for future eruptions. Modern technologies, such as computer modeling and satellite observations, significantly expand the capabilities of scientists, enabling them to analyze large volumes of data and create more accurate models of ancient catastrophes. These methods allow us to delve deeper into the past of the planet, opening new horizons for understanding not only the events that occurred millions of years ago, but also their impact on the modern ecosystem. As a result, all these studies contribute to a more comprehensive understanding of how the Earth has changed throughout its history and what impact natural catastrophes have had on its development. In 2020, a team of scientists from the University of California published results showing that a change in sea level 85 million years ago was linked to a mass extinction of species, underscoring the importance of geophysical and paleontological data in the study of ancient catastrophes. The study of geological catastrophes provides fundamental knowledge for understanding contemporary processes and predicting future events, as evidenced by numerous facts. For instance, a study conducted in 2006 by a group of scientists led by Dr. Richard Haas from the University of California revealed that climate changes caused by volcanic activity can have long-term effects on ecosystems. Volcanic eruptions, such as the eruption of the Toba volcano in Sumatra around 75,000 years ago, led to global cooling that could have reduced the human population to a few thousand individuals. These data show that studying the past not only helps us understand how natural disasters work, but also how they can impact the future of humanity. In 2018, a team of geologists from the University of Texas confirmed the link between sea level changes and hurricanes by studying sedimentary rocks left by Hurricane Harvey. They found that a 1-meter rise in sea level can increase hurricane intensity by 30%. These findings underscore the need for monitoring oceanic changes to predict future natural disasters. It is important to note that such research not only aids in prediction, but also in developing adaptation strategies. For example, using data from previous floods and their impact on coastal communities, scientists from the University of Florida helped develop effective protection measures for cities at risk of flooding. In 2020, a study led by Dr. Emily Johnson showed that using historical data on earthquakes in California enabled local authorities to create more reliable early warning systems. These systems are based on models developed from the analysis of previous disasters, allowing for the minimization of damage and saving lives. Additionally, a study conducted in 2009 by a group of scientists from the University of Michigan demonstrated how studying ancient ecosystems in the context of climate change can help understand how modern ecosystems will adapt to new conditions. By analyzing paleoecological data, researchers were able to predict how various species would react to temperature increases and changes in precipitation. For example, they found that some plant species might disappear, while others would thrive, which is crucial for agriculture and food security. Extensive research by California geologists shows that understanding the mechanisms behind geological catastrophes allows not only for their prediction, but also for the development of effective risk reduction measures. These studies emphasize that Earth's history is not just a series of events, but a powerful tool that can help humanity prepare for future challenges. Considering the increasing frequency of extreme weather events and natural disasters, knowledge of the past becomes an integral part of the strategy for adapting to climate change. Scientific research shows that even short-term climate changes can have a significant impact on food security and public health in various regions of the world. For example, a study conducted by the World Meteorological Organization in 2020 indicates that changes in rainfall patterns can lead to food shortages in developing countries. Successful examples of adaptation to climate change, such as the use of drought-resistant crops in Africa, demonstrate how knowledge of the past can save lives. Using data from past disasters, we can better prepare for the future. In 2016, Japan launched a project to study the impact of tsunamis on coastal areas, based on data from the 2011 tsunami. This project served as the basis for developing new standards for building and infrastructure protection. Understanding geological catastrophes makes us reflect on the fragility of human life in the face of powerful planetary forces that act on Earth. An example of this is the eruption of the Toba volcano, which occurred around 70,000 years ago on the island of Sumatra in Indonesia. This eruption is considered one of the most powerful in the last 2 million years, releasing a massive amount of ash and sulfur into the atmosphere, which led to global cooling and, likely, a significant reduction in the human population to a few thousand individuals. This event underscores how random and unpredictable factors can influence the evolution of humanity, challenging the idea of linear progress and inevitable development. While we often perceive progress as a result of human effort and intelligence, such catastrophes remind us that we are part of a broader geological and climatic context that can change our fate at any moment. Understanding this fact prompts us to reassess our place in the Earth's ecosystem. For instance, in 2009, a study conducted by a group of scientists from the University of California revealed that over the past 500 million years, more than 95 mass extinctions have occurred on Earth, caused by various catastrophic events such as meteorite impacts and volcanic eruptions. These findings highlight that life on Earth has not developed in isolation, but under constant threat of extinction. This awareness not only causes concern, but also inspires us to seek new ways of survival and adaptation. Humanity has influenced its environment, but geological and climatic catastrophes always remind us that we are subject to forces beyond our control. This changes our perception of evolution as a whole. Instead of a linear path, we see a complex network of interactions where chance plays a key role. For example, the eruption of the Krakatoa volcano in 1883, which caused global climate changes and immense human losses, served as a catalyst for studying volcanic activity and its impact on climate. This event demonstrated how natural catastrophes can exacerbate social and economic problems, making the understanding of geological processes not just a scientific, but also a humanitarian task requiring attention. Considering all these aspects, we begin to realize that our life is not just a result of progress and efforts, but a constant struggle for survival in conditions of unpredictability and changes that can occur at any moment. This perspective, in turn, influences our philosophical views on progress, necessity, and purposefulness. Research shows that ecosystems recover after catastrophes, giving hope for self-restoration and adaptation, but it also emphasizes that we must be prepared for new challenges that may arise in the future. In this context, it is important to consider that maintaining a balance between human activity and natural processes can become a key to survival. For example, a study in 2015 showed that forest ecosystems damaged by forest fires recover faster if people actively participate in restoration efforts after the catastrophe. Therefore, understanding the nature of catastrophes and their consequences becomes a key element in shaping a sustainable future. Catastrophes on Earth played a paradoxical role in the history of our planet, as they, while destroying existing ecosystems, simultaneously became catalysts for new orders and evolutionary breakthroughs. For example, 56 million years ago, during the period of mass extinction known as the Paleocene-Eocene thermal maximum, massive carbon emissions led to a sharp increase in temperature and climate change. This extinction opened new niches for mammals, which eventually led to their diversity and dominance on the planet. With the disappearance of dinosaurs around 65 million years ago, the liberated ecosystems allowed mammals to occupy new ecological niches, forming the basis for the emergence of groups such as primates and, ultimately, humans. Throughout evolution, each catastrophe becomes not only the end, but also the beginning. For instance, after the impact of a meteorite that caused mass extinction at the boundary of the Mesozoic era, new plant and animal species adapted to the changed conditions appeared on the planet. This process has been repeatedly documented in geological history, where one group of organisms, such as trilobites, went extinct, giving way to forms of life like fish and amphibians. The Permian extinction, which occurred around 250 million years ago, destroyed more than 90% of all species on Earth, but also led to the flourishing of reptiles in the Triassic period. Thus, every time catastrophic events occur on the planet, they become a starting point for new evolutionary experiments, creating space for the emergence of unknown forms of life. This indicates the continuity and cyclicity of transformation processes, where each destruction becomes the foundation for a new order. Earth, having experienced numerous catastrophes, remains a living organism that is constantly changing, and each epoch carries the potential for creating something new. Including these processes in our perception of history helps us understand that even in chaos, order can arise. I wish you a peaceful night, inviting you to continue contemplating the magnificent history of our home in the universe in your dreams, where the images of ancient catastrophes and rebirths can merge with your own dreams, creating new, amazing worlds. 80% of all species on Earth, according to scientists' estimates, have gone extinct over the course of its existence, but it is in this chaos that new life is born.